minutes starts when the session officially starts, right? So because we're already 9:02.
And if Patrick stands up, then
Oh, okay. I think now. Hello, everyone, and welcome back. This is Thursday, the third day of this SQA conference, and it's my great pleasure to be the chair for the next session and the first session of the day, which is fluxonium qubits and bosonic qubits. And we will have three high-profile presentations. And the first speaker will be Christian Anderson from TU Delft. It's an invited talk, so we will enjoy 20 minutes, including questions. And then we will have two contributed talks with 10 minutes plus 2 minutes of questions. Christian, please. Uh, Exactly. Christian will talk about towards large-scale architectures for fluxonium qubits. Please take it away.
Great. Thank you very much, Patrick. And thank you very much, everybody, for coming in this morning and attending SQA this year. So I will talk about towards large-scale architectures for fluxonium qubits. Yesterday, we also saw a very nice talk from the Munich group where they showed the first wait for connectivity for fluxonium qubit. Here's a teaser on what hopefully comes next in our group. So maybe we can be second in having a connectivity for fluxonium qubits. And I will talk a bit today about how we will get there. But before really getting into that, people who have seen me give presentations before have seen this slide before. And I want to always remind ourselves that this is very, very important, that we understand that we are trying to build a quantum computer. And that's very, very, very hard. It's not something we just do. It's hard. And we actually don't really know what is the best way we build a quantum computer. And that's why we keep exploring new ways we can build quantum computer, exploring different types of qubits. So most people in this conference work with transmon qubits. But the reason why we are interested in fluxonium qubits is we need to try all ways we can actually build a quantum computer. Otherwise, we will never get there. So we focus on fluxonium qubits. A few reasons we like fluxonium qubits. If we look at the schematic of a fluxonium qubit, it almost looks like a transmon. We have a capacitor, we have a Josephson junction, and we have an inductor. The inductor is sort of the different part compared to a transmon. And if you flux bias at half a flux quantum, you get this very characteristic double well potential where the ground state and first excited state are the even and odd superposition of sitting in these two wells. And that gives rise to a qubit that has a very large anharmonicity because you see the 2 state and the 3 state are very far away from the 0-1 state in frequency. The actual qubit frequency is very low, so few hundreds of megahertz, which gives rise to a potentially high lifetime, partly because it's a low frequency and partly because the matrix element of the charge operator is smaller than for a transmon qubit. So this potentially gives you a very, very nice qubit. And if you sort of look in literature, people have shown that this can have some properties that are very nice. Single qubit gates have been demonstrated with up to 99.99% fidelity, which is pretty good. 2 qubit gates have been demonstrated with more than 99.9% fidelity, and many works show 99-point-something% fidelity. The first one really showing above 99.9 was this work from MIT here. And readout is lagging a little bit behind, but there's some promising directions also. What I will talk about today is sort of ways you can engineer 2 qubit gates. So there's different approaches. And you need to really think about how you do your 2 qubit gate when you think about how do I want to scale to many, many qubits, because that really dictates the architecture you're going for. So in this work from MIT and also in our work from last year, was published now this year, we went for an architecture where we have a fluxonium qubit and a fluxonium qubit coupled by a transmon. So in our case, it's this T-shaped transmon. In the MIT work here, they had an X-shaped transmon as a coupler between two qubits. And the reason why we went for this architecture is that directly coupling fluxonium qubits to each other is a bit challenging for the same reason why we have very good or potentially good lifetime of the qubits. So capacitive coupling between fluxonium qubits is suppressed partly by the small matrix element of the charge operator. So you need to find a way to sort of circumvent this. And one approach is to use the higher excited state of the fluxonium, so the 2-state and the 3-state, and make them interact with something. And that something in this work is a transmon qubit. You saw the nice work yesterday from the Munich group. They used a resonator as that something, but here we focus on having a transmon as the coupler. Now, when you then do have this extra element as a coupler, you can start to do 2-qubit gates using that coupler element, using microwave-only signals. And that's very nice because essentially the fluxonium qubit is really only a good qubit if you sit at sweet spot. That's where you have the symmetry and the protection. So you don't really want to do flux pulses to go away from the sweet spot. So microwave-only gates is a nice way of keeping the protection while having a good 2-qubit gate. And in this scheme, we can do microwave-only gates by driving the transmon. So to understand how this really works, if you sort of look at the energy diagram of this system with 2 fluxonium qubits here in blue and the transmon in green, we have the computational basis states, so the 0, 0, 0, 1, 1, 0, and 1, 1 states here for the fluxoniums, and then with the coupler, the transmon here in the ground state. So these are the 4 states. And then you could imagine you could excite the transmon. So we have sort of the replica of those 4 states up here with the transmon excited. And the transition going from, for example, 101 to 111 is different than the transition energy going from 001 to 011 and so on. So we can selectively drive, for example, 101 to 111 and back again. And when you do this 2-pi rotation, you pick up a minus sign, but only on one of the states. That's a conditional phase gate, CZ gate, so that's a 2-qubit gate. Very nice. Does this work? So we did that. Here there's sort of 3 different colors. Let me start with the simplest one, which is just the cosine shape. So we just do a very simple cosine shaped pulse on the transmon. It's essentially just doing Rabi oscillation on a transmon qubit. We know how to do that. And if we do that, we get sort of almost like 99% fidelity gates. You see the gate time here is sort of few tenths of nanoseconds, let's say 60 nanoseconds, where we get the optimal gate. That's quite a bit slower than single qubit gates on a transmon, even though it actually just is a single qubit gate on a transmon. And that's because there's other transitions that you drive. So if we go just a little bit back here, so we want to drive this 101 to 111 and not all these other ones, but they are different in frequency, but not that much. The frequency difference is sort of tens of megahertz. So you need to avoid those. And that's sort of what hits you if you try to drive too strongly. Then, of course, it's a frequencies transition we don't want to drive. And then we know how to avoid driving a single transition. That's called drag. So if we start adding drag to our gate, we can do a little bit faster. Fidelity here doesn't really improve that much. Here we are mostly limited by the T1 of our coupler, which turned out to be very bad in this experiment, like 1 microsecond, but okay. We can still do slightly faster by doing this drag. And if we want to do even a little bit faster, we can do a technique called fast drag. That was something that IQM demonstrated for single qubit gates of transmons. It's essentially drag, but where you select more frequencies that you don't want to drive. And then you can again go a little bit faster. Although again, the fidelity doesn't really go above 99% in our experiments, but this is sort of the scheme that we came up with. And now, okay, we did a 2-qubit gate, but we want to scale this. That's sort of the main motivation. Yeah. So can we scale? And for that, we did a theory work that was recently on arXiv. And we were trying to say, okay, if we just take this approach and scale it, does it really work? And we sort of started with sort of the two examples here. So reference one here is the paper from MIT that got 99.9% two-qubit gate fidelity. And reference two here is our work. And if you just sort of naively scale it in a 1D chain, you can sort of end up with a frequency configuration that looks a little bit like this. So here, what I'm showing is fluxonium qubits in green, and then transmon couplers here in blue. And what I'm showing here in the frequency scheme is not the qubit frequency of the fluxoniums, but the 1-2 transition and 0-3 transitions, because those are the ones that then interact with the transmons here as couplers. And if you then simulate what is the gate fidelity, if you calibrate a gate with all the other qubits, so here we calibrate a gate between the two middle fluxoniums, so fluxonium 5 and 7, using the coupler 6. So we put the spectators here in 0, the spectators over here in the 0 state, we calibrate a gate, and we can numerically calibrate a very good gate with like, well below 10 to the minus 3 error. So that's pretty good. But now something interesting happens, which is that if these other qubits, so the qubit 1, qubit 3, qubit 9, and qubit 11 were in sort of random states, so one, the excited state, for example, and we then try to do the same gate that we calibrated with the spectators in 0, then the error is very bad, to the degree that this is just useless. It's like 10% of error, which is really bad. So we have to deal with spectator errors. And that's also something that was mentioned in the nice talk yesterday. And one approach is to come up with a frequency scheme where the sort of nearest neighbor transmon, you dynamically tune away from sitting near, for example, the 0-3 transition, and then you flux it down in frequency to some lower frequency, such that there's this staggering architecture between the nearby transmons. And if you do that, you can again calibrate your gate with spectators in 0, and then when you repeat it with the spectators in other states, you remain in a reasonably good gate. And you can again, you can then try to do this a bit more involved with sort of 2D architectures. So we also did that, and again, we see very good gates when we calibrate in the 0 state, and when the spectators are in random states is a little bit worse than when in 0, because now there's a lot of neighbors, but it remains pretty good gate, like 10 to the minus 5, I think we would all be happy with. So this is a way where we think that, okay, we think we could, in principle, scale this architecture to 2D grids, provided we can really engineer all of these fluxonium frequencies and transmon frequencies pretty well. One thing I wanted to briefly mention is to actually do these calculations, it's actually pretty challenging, because each fluxonium, if you want to do this accurately, is a 6-level system, and the transmons are 4-level systems, which means that the Hilbert space for this 2D grids is huge. So huge you cannot just do it on a laptop. So what we instead had to do to really do this is we developed our own custom MPS algorithm to deal with this. And if you read the paper up here, we have full open source package where you can redo this at home if you want to try different frequency configurations. So this was sort of our first approach. We demonstrated the 2-qubit gate, and now we think we know how to scale it. But it does maybe look a little bit complicated. I admit that. So we could also think about, can we do something a little bit simpler? And what's the simplest thing you can do, which is you just don't have a coupler and you just couple 2 fluxoniums directly. I said earlier that that's a little bit challenging because you actually have smaller coupling, but maybe it's good enough. So let's try to explore that a little bit, but keep in mind we still want to do a microwave only gate. We don't want to start fluxing our fluxonium qubits. So the approach here is to consider a fluxonium here in blue that we call the control qubit. And then in orange, we have a target qubit. And then we drive the control qubit at a frequency that is close to the target qubit. So we drive this qubit at the frequency of this. So you see the drive pulse is orange, just like the target qubit. And that's called a cross-resonance gate. It's something that has been done a lot for transmit qubits. And now we want to explore that for fluxonium qubits. There was a work from the Manouchian group already showing this for fluxonium qubits, but we wanted to explore it a bit more in depth. So if you do a cross-resonance gate, you can prepare your control qubit in either 0 or 1. And if you then look at your target qubit, you get Rabi oscillations that now depend on the state of the control qubits. The rate at which you get this conditional Rabi, you can sort of write as the coupling here times the matrix elements of the charge operator, and then this delta P, which actually took quite an involved math to derive that you can read in this paper, so I wanted to write it out. It looks a little bit wonky notation here. So this is the charge element of the one state, and this -1 means that it's the first Floquet mode in the driven system. So what you should think about is that this means how much does the charge oscillate at the driven frequency when you're in the one state, minus how much does the charge fluctuate when you're in the 0 state, when you drive the system. So this is what we call the conditional polarization. And if you calculate it, you see that this can actually be up to amount 1, which means that you can kind of do a cross-resonance gate at the same speed as a direct exchange interaction here, which is nice. What is interesting though, and this is very, very sort of fun physics, is that you cannot just drive infinitely fast. At some point, this conditional polarization actually saturates if you do the full Floquet analysis. And that's something you cannot just approximate with perturbation theory. If you do that, you just get sort of a whoop. But this point is something that you can find with numerics. And depending on what is the actual target qubit frequency, sometimes you have these like weird interactions, and sometimes it's not as smooth. But there's always an optimal point that we could then find. So let's do this experimentally. So this is a device. We have 2 fluxonium qubits in blue and orange, a capacitive coupler in green. And if we then do this, we measure our conditional Rabi rate. So here we drive the control qubit at the target frequency, and then we look at this conditional Rabi rate. We see that we get sort of a maximum rate that is slightly more than this ice-drop rate, which is what you would expect. So that's a delta P slightly bigger than 1. And if we take this model that I just showed before with no fit, and we put this on this, we get a curve that just matches the data, which is very nice. So this I find very, very interesting. So when you can do things where the model just matches your experiments without too much effort, that means you actually understand what's going on. So now we can just go to this point and do a 2-qubit gate. And hopefully that's then a good 2-qubit gate. So we did that. And so here we have gate duration on the x-axis. We have the fidelity or the error on the y-axis. And we just increase the drive strengths, which means we go to shorter gate durations. And this point is sort of the maximum we can do. So again, we cannot really do faster because we actually have a maximum rate, but that's sort of around here. So a gate duration of 48 nanoseconds, where we have a gate fidelity of 99.3, which is pretty good. How well is this gate then actually? To really answer that question, you should compare to the decoherence rate. So if you just benchmark an idle gate, you see that for the short gate times, we are following the idle gate, which means we are mostly decoherence limited. Here we have some coherent errors, which we also understand because we did all the theory. So we also know how to deal with it. We just do a small echo, so we cancel these coherent terms. And then we recover this gate. Now the gate is a little bit slower because you need to sort of stop, do an echo, then start again. But we still match sort of the decoherence rate. Does it scale? I will talk this very briefly, but yes, it does. So we considered in this theory paper different architectures, so a square lattice, a hex lattice, and a heavy hex. And we tried to see, would this gate in principle work without any obvious frequency collisions? So we calculate what we call the zero collision yield, which means we target some frequency configuration. There should be no coherent errors, but now we have some uncertainty in our EGA. And if you can target your EGA with a few % precision, you should be able to scale to distance 21 error correction code, depending on the lattice, within a few % of precision in your EGA. So that looks very promising, and it's, to be said, orders of magnitude better than if you would do the same calculation for cross-resonance gates for a transmont device. So that's pretty cool. So now we are trying to do the next steps, which is to do a weight 4 cross-resonance architecture, and hopefully that will work soon, work in progress. So this is a teaser. Before ending, I just want to flash 2 other things we did with Fluxonium qubits. So we had this work that was published earlier last year, which is on single qubit gate. So something interesting happens if you drive a Fluxonium qubit, because it's a low frequency qubit. You actually break the rotating wave approximation relatively easily. So that's fun. You can read that paper. And one thing that happens when you do readouts is you sometimes have measurement-induced state transitions in Fluxonium qubits. And we did measure that, and we did some branch analysis to show that we actually understand it. So you can read about that in this archive paper. And with that, I want to thank the team, in particular Eugene and Jinlun, who is here today, and Martin, who is just handed in his thesis. So with that, thank you for your attention.
Thanks, Christian, for these really exciting insights into how we can scale Fluxonium processors. We have time for one short question. Maybe we start with Andreas.
Can you explain once more what was special about the frequency configuration that you found with your theoretical method in the beginning?
Yes. So the main thing that is special here is you need to sort of stagger the couplers. So that's very important. So the thing we realized is that the spectator errors is not so much between the Fluxonium qubits themselves, but it actually is between the couplers. So you really need to think about the configuration of the couplers. So it's maybe not super deep when you sort of know that you need to stagger the couplers, then you just do that. But it was sort of the insight was that the spectator errors actually come from the couplers. So that's what you need to think about.
All right, let's thank Christian one more time, please. Our next speaker is Lukas Splitov from Chalmers University, and he's going to talk about linear beam splitting of large bosonic states in a multi-mode superconducting platform. Please take it away.
Hi, good morning, everyone. I'm Lukas. Thanks for reading out the long title, which I'm trying to break down to you. Some of the arguments that I'm going to cover in my talk have been covered by Christian just before, so feel reminded by what I say. This was work done here at Chalmers in the 222Q lab led by Simone Gasparinetti, and I'm excited to talk here at this home conference to you. In the 222Q lab, we work on 3 topics: quantum computing with bosonic modes, quantum thermodynamics, and quantum enabling technologies. You can think of 2-pass and switches maybe. And today's talk will cover the first matter of this list, quantum computing with bosonic modes, which takes us on a slight detour from what we've discussed throughout the rest of the conference so far. So most of you will be familiar with the standard approach, in quotation marks, which maybe starts from a transmon, which we see as an anharmonic resonator. And we typically, I don't know, you don't see the pointer, right? But we typically use the lowest 2 levels in this potential for our computational subspace. And I don't dwell on this any further because you're familiar with that. But in contrast, we can also explore a different field where we use linear cavities instead, which brings us to continuous variable quantum computing using large bosonic states in harmonic oscillators, where there's a linear or a constant level spacing between all these levels here. Prominent examples are cat qubits explored by Alice and Bob, or GKPs by Nord Quantique, and there are lots of research groups exploring this, including us. This is interesting because the harmonic oscillator immediately allows us access to a large Hilbert space, giving us access to computational complexity. Those implementations hold the promise that they allow for resource-efficient quantum error correction due to a single loss channel, which is photon loss typically. But engineering this to a larger platform is a challenge, which we've taken up in the 2-2Q lab. We're here considering a platform consisting out of 4 bosonic modes denoted as A1 to A4. They all share a same common coupler C. In order to do state preparation and readout, we think of transmon qubits as ancilla for these 2 operations in the photon number selective regime. But in order to determine the properties that the coupler actually needs to fulfill a complete universal gate set, we need 2. Linear interactions of the type A dagger, AI dagger, AJ, yielding beam splitting or swap interaction of this type, as you can see here, with beam splitting being half of the I swap. And together with single mode squeezing, this allows for Gaussian operations. But that's not enough yet. We also need non-Gaussian operations, maybe of the type of photon splitting and merging, described by an interaction Hamiltonian that looks like this: AI dagger, AJ dagger, AK plus emission conjugate. Or this also allows for multimode squeezing, leading to tri-squeeze state potentials, which are interesting for the as a computational resource, and that together allows us then to build a universal gate set. Now, the question that we need to address here is, what does the coupler look like that can enable both of these 2 interactions, so these linear interactions and these nonlinear interactions, at the same operation point? And we thought about this carefully. We thought about transmon couplers, which have been explored in the literature, or squids, or snail couplers, composed out of various sets of Judson junctions. But all of this didn't allow us enough tunability of the nonlinearities to obtain and achieve our goal. Instead, we wanted to go one step further, and the solution was to add a second loop. So the 2-loop topology, consisting out of a central branch of 3 junctions with large EJ on the order of 400 gigahertz, and 2 small junctions to the side, EL and ER, give us the flexibility that we need, as I show you in a minute. They are controlled, the properties are controlled by phi left and phi right, but throughout the talk I will prefer to talk about the sum flux and the difference flux between these 2 loops, controlled by flux lines at the top, and we'll actually make it a resonant element by shunting it with a capacitor. Now, in order to obtain and understand the properties, we first do a Taylor expansion of this potential at various different flux points, and we obtain the nonlinear coefficients, G3, G4, Gn. Now follow me along the blue line, which is along phi minus, the difference flux, at the sum flux of 0. That's the blue line here. And interestingly, and for symmetry reasons, it is exactly 0 along the phi minus, there is G3 exactly 0 along this axis. And for G4, we find that there is a point in the flux axis where it also cancels exactly. We can understand this as an interference between the nonlinearities coming from the big branch in the center and the small junctions to the side, which is exactly fulfilled at this condition here. Taken together, we can say the 2-loop topology tunes the nonlinearities. It cancels all odd static nonlinearities and the 4th order static nonlinearity. This in turn, and taken together, means that the coupler that we've just realized has no self-curve. That's interesting for the driving. And also the cavity to cavity cross curve is vanishing, or at least very minimal. What remains is a talk about the drive activated interactions that we're after. And if we do this expansion, we actually find that the drive along the phi minus axis via the G2AC element in this expansion allows us for frequency selective interactions at the sum or the difference frequencies of those modes. And taking this one step further, driving orthogonally along phi plus with a different element allows us to implement selectively three-mode interactions at sums or differences of these three modes. And this is what we want to explore further. Well, there's a lot to talk about. This talk is primarily about the beam splitting interaction. Now, speaking about the device implementation after talking you through the entire theory and our considerations. At the heart of it, as I said before, is the coupling element here. To it are connected 4 bosonic modes labeled in or colored in blue as quarter wave resonators that are then dispersively coupled to ancillar qubits, split mons here in green, and those are read out via readout resonators in purple. 2 flex lines coming from the top control the properties of the coupler. The coupler is implemented as an interdigitated lumped element, resonator element, shunted to ground via this maybe to some of you slightly obscure looking junction element, which is an ATS, an asymmetrically threaded squid with standard Manhattan junction you're all familiar with to the side and big overlap junctions in the center. Very important, and this goes back to Christian's talk before, is the mode allocation. So we intentionally place the cavities right at the bottom of the frequency spectrum that's available to us between 2.5 and 4 gigahertz for a given Q that maximizes the T1s that we want to obtain in our operation. To set the interaction strengths with the coupler, we define the coupler band somewhere between 5.5 and 6 gigahertz, and the coupler disperses versus flux, and hence it's a band that I need to denote here. Qubits for control and readout resonators are placed above. As I said before, and interesting for the operation is the choice that we operate in a photon number selective regime between the qubit and the cavity. And the cavities here in this configuration come to about 20 to 30 microseconds, which corresponds to a QI of maybe up to 1 million, which can certainly be improved, and it must be improved if you want better performances here. The frequencies of the cavities cannot be chosen arbitrarily, but they need to be chosen with care. In order to have very selective drive frequencies here, for 2-mode interactions labeled with colors, we need to go through all the different combinations of modes that are sums and differences that we can think of, both for the 2- and 3-mode case, and we need to make sure that none of these interactions that are enabled actually collides. And while we tried our best in our design to avoid this, after fabrication shifts, there's one or there are 2 transitions that actually collide in the spectrum. But otherwise, the frequency allocation here, the drive frequency allocation, worked out fairly well. Moving on to the characterization of the interactions. Okay. So we're able to create a coherent state here, run an interaction, measure the FOC1 component, and obtain a coherent oscillation between these 2 modes. We see that we're readout limited on the one side, and we're bound by the input state on the other side. We measure, from this we extract the beam splitting coefficient versus flux, and we see that at around 0.5 flux, the beam splitting rates all max out. Now looking at the efficiency, the population transfer efficiency versus flux, we see that the efficiency peaks at the maximal beam splitting rate and not at the curve point that we found so interesting before, which is limited, or just an indication that we're limited by the cavity T1. So in numbers, we created all-to-all I-swap operations at an efficiency of 97% with a gate time of 400 nanoseconds, and we're cavity T1 limited. Given the remaining time that I apparently have, I take you straight to the conclusion, which is we have realized this multimode bosonic platform with all-to-all connectivity. We've shown beam splitting interaction. We've studied the lost channels, and in fact, I couldn't show you the nonlinearities that we've discussed on another slide. So here we have at the curve point and in this spectrum, 2-mode and 3-mode interaction capabilities, which we find very interesting for a multi-mode platform as such. And going forward, we need to urgently tackle the T1 of our cavities and the T2s that are inherited or limited through the T2 of the coupler. If you want to discuss this further, either talk to me after this talk, check out our GitHub page where we discuss the design of such a multi-mode platform, or check out the group website. But also 2 of my colleagues, Shu and Kuman, are presenting posters this afternoon to discuss this in greater depth. So, thanks for your attention.
Thank you, Lucas, for this exciting presentation, and the fact that you decided to use the ATS, I think, confirms that you drew the right conclusions. We have time for one short question. Yes, please, here in the front row.
So, okay, very simple question. Why do you need 4 cavities? If I just want to implement simple beam splitter, I would need 2 bosons. Probably will it be easier? For example, if I'm thinking about like quantum simulations of systems where I have fermions and gauge fields, I would need only simple beam splitter between 2 bosonic modes. Would it be simpler?
I mean, we consciously decided to implement an architecture with all-to-all connectivity between 4 modes because we had a certain application in mind, which is boson sampling. I didn't speak about this given the time of 10 minutes, but the idea here is to prepare FOC1s or large bosonic states in a selected set of these 4 cavities, and then operate simultaneously as a beam splitting operation between 2 pairs, for example, of these cavities, and do this sequentially over different combinations of those to obtain a Haar-random unitary. And we intended to sample from this distribution ultimately. So that's the motivation for this all-to-all connectivity. But I also think that there are applications beyond that, running some near-term quantum algorithms. But what I want to say is that this architecture could also be adjusted to a hexagonal grid and extended to full lattice.
All right. Thanks for the question. Thanks for the answer. Let's speak Lucas one more time, please. Now we come to our third and last speaker of the session, which is Kerem Yurtseven, and he's going to talk about bias-preserving entanglement of Kirkhead qubits with an ATS coupler. Please take it away.
Yeah, thanks for the introduction, and hello everyone. I'm Kerem. We are quite an international group, and today I will quickly present our work on bias-preserving entanglement of Kirkhead qubits with an ATS coupler. I'm quite lucky because we listened to a very nice presentation on bosonic modes and ATS. So I will go directly on what are Kirkhead qubits and how we stabilize them and why we need a bias-preserving control X-gate. So firstly, we align our coherent states on the z-axis, which allows us protection against bit flips. And the important thing about the Kirkhead qubits is how we stabilize them. To stabilize, we use the kernel linearity with a 2-photon drive, where I wrote the Hamiltonian in a compact form here because it will be useful later, but you may think the alpha here as the square root of kernel linearity and the ratio between kernel linearity and the 2-photon drive. And by using this Hamiltonian, we get the protection directly in the energy spectrum in phase-to-phase. And this allows us a strong bias when also allows us to realize fast gates compared to other types of cat qubits like dissipative gates where the stabilization came from the lost channel. But the problem is we have the stabilization, we can apply the single qubit gates, but we need a 2-qubit gate where the control X-qubit gate to realize quantum error correction or entanglement, and the problem that the naive classical control X gate doesn't commit with the dominant error channel here, which is phase flips, and any phase flip that can occur during the gate can be transformed to bit flip, which kills our bias. So there is good theory work from Yale, Shruti and from also the Paris group, Juliet, where we, instead of flipping the cat state, we rotate the cat in the phase space, and by doing this, we can commit with the error and the bias is preserved. So here the theory is well established, and also the Hamiltonian to establish this theory, to realize this theory is good prepared, but what we are trying to do is how we can do this in a real experiment, in a real circuit. So as you may see here, we have some kernel nonlinearities and squeezing terms to stabilize, and also we rotate the cat in phase space by changing this phase of the two-photon derive, but we can categorize our terms in a different way to make it more realizable in a circuit. So the green ones are kernel nonlinearities and squeezing terms just for stabilization, which are not our concern here, but the two important interaction is multi-photon exchange between target and control mode, and also conditional displacement on the control mode conditioned on the target mode. And what we propose is using an asymmetrically treated circuit between two resonator modes, where we just omit the stabilizer for both resonators, and by using the nonlinearity of the ATS Hamiltonian, by engineering the ATS Hamiltonian, which we see here, we can get our target interactions. For this, we use the pi over 2 flux for both the common flux and the differential flux, and we also apply a RF flux on the common mode. And by doing this, we can just, for simplicity, neglect the non-idealities of the ATS, like the delta EG or EG2. And when we expand our sinusoidal term with Taylor expansion and going into rotating frame, we can choose our frequencies to exactly activate our desired terms. And as you may see, for the multi-photon interaction, we need a frequency in 2 omega minus omega b, and for the displacement interaction, we just need the omega b. But here the question comes, is it like simple as this? Obviously not, because in the Hamiltonian, there is not only the G3 and GCT terms living. There are other on-resonant terms and also off-resonant terms with strong amplitude, which can just destroy your interaction terms. And to do this, we implement an active compensation for especially the displacement terms, because as you can notice, the linear terms, first order displacement terms, are at least one order of magnitude higher than our desired terms, and they can just kill everything we try to do. And for other off-resonant and on-resonant terms, they are more negligible in amplitude and also optimized by the circuit design. And to compensate these undesired condition, displacement terms, we apply an additional differential RF flux, which changes our Hamiltonian to with an addition of a linear displacement term. And this just gets rid of all the first order displacement terms, but additionally, we can also use the photon number equity for coherent state. Since we are assuming we are in a good stabilized mode, we can just add another coefficient based on the photon number, where we can get rid of the higher order conditional displacement terms as well. So by doing this, we just establish all the deriving scheme, and now we show some results on how we can, what are the resulting schemes. So first, for a sanity check, we realize the conditional displacement interaction. As you may see in the second figure, the position of the second mode, the control mode, change conditioned on the number of photons in the mode A, which is exactly what we desire. And for the multi-photon exchange, the two modes in the target qubit, the mode A, just exchange into mode B. And after doing this, we add other stabilizer terms in theory, in ideal versions, and then we just made another sanity check for 50 nanosecond gate time to realize the control X gate. And as you may see, if the target is in state 1, control is state 1, target changes state. If it is 0, and it's stateless. So for further characterization, we apply a gate tomography. Here you see the pilot transfer matrix under no loss for two gate duration, 50 nanosecond and 100 nanosecond. And we then transform these into Chi matrix and obtain our fidelities as 99.7, higher than 99.7 even at the 50 nanoseconds. And all the infidelity comes from, half of the infidelity comes from the phase error of the control qubit, and the other half comes from the leakage out of the cut space. And then we add a loss, we add a considerably strong loss to stress test our bias. And we see that when we obtain the error channel Chi matrix, we see all the errors accumulate on phase flip type errors, which is the exact thing we desired. And here you see some gate time sweep. As you may see, if we go to higher gate times, our infidelity drops and fidelity improves really well. And at the higher gate times, our bias also gets very close to ideal cases. And for the 50 nanosecond gate duration, we obtain nearly 600 times higher bias than the NEU case. And for another metric to make it more understandable, we apply repeated gate times and measure the flip time under two different cases. First, to measure the bit flip time, we prepare our initial state as 1-1, and then for control X, we apply the gates twice, and for idling, we just apply the stabilizer. And similarly, for the phase flip, we just start in 1+ state and see the evolution. And after we get the results, we see the consistency between the gate tomography and the time evolution methods, and the significantly longer bit flip time shows us the bias preserved. So in this work, we showed the 50 nanosecond high fidelity and bias preserving control X gate between two Kerr-Cat qubits with a really strong bias. And the main purpose of this work was to identify the ATS non-idealities, the loss channels, the error sources to make it to prepare for the experimental demonstration of the proposed circuits. And now we are looking forward to it. And yeah, thanks for listening. I am open for any questions.
Thank you, Karen, for this interesting presentation. Do we have questions? So then I have a question for you.
Yes, Sergio.
You want to use a Kerr-Cat architecture, but in your circuit diagram, you're using linear harmonic oscillators. So I'm assuming they are inheriting the nonlinearity from the ATS mode?
Not from the ATS, as I said, we just omit the stabilizer terms, and probably we will use a snail additionally coupled to resonators to grant them the Kerr nonlinearity.
I see.
Yeah.
Okay. Then let me ask a second question.
Yes.
In your proposal, you're already including some non-idealities in the
Yes.
ATS that we know of. But here you're approximating the central inductor with an idealized linear inductor. When you implement this with a junction array, for example, can you still ensure that the flux allocation that you need for the cancellation of this linear displacement is actually correctly modeled?
Yeah, it depends. I mean, like, we modeled it as well, and what we see is there are some strong cross curve, and it is like a nonlinear cross curve. So it just shifts the frequencies a lot and kills the process. But the good thing is the cross curve is also conditioned on the photon number, and the photon number is, as we discussed later, constant for coherent states, and then we can shift the frequencies of or new based on the fabrication and just get good results. And we also showed it, and you can check the details. We will just publish the preprint soon. Okay.
Excellent.
Yeah.
Excited to read more about it.
Thanks.
I think we come to the end of this session, so I would like to ask you to thank all of the three speakers again. And I'm happy to give the mic to the next chair of the next session, which seamlessly will continue in this room.
Thank you for the participation of this session. Next coffee break is 11:15. My name is Marcus Coronetti. I'm assistant professor here at Harvard. Next session, it's a short talk about electromagnetic radiation. Thank you. It's a pleasure to be at this conference. It's a very nice conference. Good to see so much focused talk on superconducting qubits. So Q control does not make hardware. And as Christian said, there's quantum computing. Building a quantum computer requires a lot of new ideas at different layers of the stack. What we focus on are two parts. One is controlling today's quantum computers. So that's something that you all showed yesterday, where we did a Fermi-Hubbard simulation on current devices. Today, I want to talk to you about what are the different new hardware knobs that we can turn and which will have big impact on making a quantum computer work. Let's see, good. So if you think about different modalities and take a step back from just focusing on superconducting circuits, different qubits and different modalities have different benefits. So here I list some examples. So you can care about, or do you have long range interactions? That's something atoms and ions have very naturally. While on superconducting circuits, 2D architectures like the one Andreas showed 2 days back are most advanced, and there are new works coming up for QLDPC cores, but there is a lot of uncertainty on implementing them effectively. Whereas the good thing that works for superconducting circuits is their speed and high gate fidelities. So this is something, so one can ask the question, is it possible to effectively use different qubits together? So, but let's ask a question, is that really necessary? And to give you a punchline to what you could get by doing that, here is a plot of resource requirements for RSA 2048. It's one of the applications that many people are interested in. So on the x-axis, you see the number of gates, so the number of physical qubits you would require. On y-axis, you see how long it would take. Sorry, it's other way around. What on the top right, you see basically that you would take longer time and more qubits, and bottom left is where you want to go. So here I plot some of the works that have come up recently and over last almost a decade. And you will see that, so the work that we focus on is this here, Gidney's work from last year, where he showed he can do within 1 million qubits on superconducting circuits within like 5 days or so. Without changing algorithm, we are able to get an improvement by using different qubits together. And this is something important because there are different ways you can improve. So you can improve your algorithms, you can improve your qubits themselves, or you can think about different architectures and interconnects. So it's a question of where do you want to put the risk, or where do you want to put the requirement for advances to make further progress. So here, this talk, we are looking for advances in the interconnects from a hardware point of view. And then if that happens, we look at how can we leverage that. So here is our proposal. This all the things I'm mentioning is already out on archive. So this is our vision for the architecture. As you can imagine, the word heterogeneous has been overloaded in the community. So there are different meanings of it. You can think of heterogeneous functions of your different parts of your quantum computer. You can think of heterogeneous modalities of qubits. You can think of heterogeneous cores themselves. In this case, we take it to the other extreme, where we look at heterogeneity of all kinds working in tandem. So what does that look like? And the architecture is very similar to today's classical computers. So here we have, imagine QPU models at the bottom left, where you actually have like small sized QPU modules whose task is to be very fast and have universal gate set. They don't need to have necessarily long memory times. Um, and the and then the T-state factories or magic state factories essentially only need to be connected to this QPU modules. Now you can have a bunch of those, but their size in itself does not need to scale with the algorithmic size. On the other hand, we also look at hierarchy of memory. So we look just like in your a classical computer, you might have cache, you have RAM, and then long-term storage. Here we look at two specific kinds of memories. One is short-term quantum memory. We call them STQM. For this talk, I'll refer to them as cache. And then we have a bit longer-term memory we call random access quantum memory. I'll just call it as RAM for now. And essentially, the main difference is that for short-term memory, if once you start leveraging atoms or ions, which have much longer coherence time compared to the cycle time of your processor, you can actually get away without doing active error correction on those atoms for short periods of time. So that's what I call by short-term memory. And similarly, on the Rackham side, it's more traditional. You do error correction on those memories, but then how you transfer information gets a bit constrained there. So, and then lastly, we also imagine that for specific applications, you would have some application-specific quantum processing units, where essentially, let's say you want to have a submodule of adder within your broader circuit. You specialize the connectivity of your logical qubits and how everything works out, and that chip basically, or that module basically gets multiplied. And depending on what you care, you could have different kinds of modules. So the point of this is that this is an architecture which is fairly generic. It's not customized for a particular algorithm, but already it starts giving computative results to, for example, the Gidney case, where it is very hand-tuned to RSA 2048. So, okay, great. We want to have different modalities, but then we also think about like how long it takes to do error correction. Typically, the error correction time for each cycle between, say, superconducting and atoms or ions is 1:1000. So just imagine if you now directly try doing lattice surgery to measure parity between the two qubits, you would have to do 1,000 cycles on your superconducting circuit just to while one cycle happens on the atoms. And that to me, like upfront, it seems very daunting, and you wonder whether you'll ever get anything out of it. But actually, later you'll see that actually you can get something out of it. So here we actually show two different examples of transfer of information between two modalities. So one is transversal teleportation. So how we do, basically imagine you have entangled bell pairs across these different frequency bands. You send it over, you purify them, and then once they are there, you do classic like teleportation approach for each data qubit individually. So you move each data qubit from your QPU to your memory and vice versa. That's one approach. Of course, the requirement here for hardware is even more, because on your superconducting circuits, now you will need for every data qubit some kind of way to connect it to a coupler outside where you can talk to a photon coming in. It sounds a bit hard, but then imagine you don't need this for every data qubit. You only need it for some adapter. So it's almost like an adapter that exists. But the benefit of that is if you can achieve that, your transfers, your teleportation actually is not dependent on the size. On the size of your logical qubit distance, or the time of your clock cycle on the atomic side as well. On the other hand, let's say it's hard to do that. We also consider more traditional, like a more conservative approach of, say, doing just lattice surgery across these different ways. And in this case, you only need bell pairs across the edges. but you need to do now D rounds of those. So it's a trade-off of time versus hardware complexity. So one way to understand how exactly it works, we go beyond just counting T states and actually do end-to-end compilation and resource estimation. So basically, we actually schedule every operation up to a clock cycle. So like every physical single or 2-qubit gate, we put in the typical numbers or durations required, and we do the complete calculation. So we have a complete compilation pipeline. I won't go into the details, but you can think of it as you give it an input circuit, you give it the code parameters and whatever you care about, and it gives you all the resource estimates. So how does it look like? So here you see we tested across 3 different algorithms: QFT, adder, and Fermi-Hubbard model. And typically you see that with the size of the algorithm, we see a consistent improvement. We see orders of magnitude improvement, even just up to 1,000 qubits. We see reduction in the number of physical qubits required. And most importantly, the total wall clock time actually is not much worse, maybe 10% worse than the pure superconducting approach. And here is maybe a bit more holistic way of looking at resources, not just counting physical qubits and wall clock time, but also asking how many couplers do you need? Because the benefit of having this functionalization is in your memory qubits don't need to talk to each other. They can be separate. And you also don't need too many operations. So that actually gives you a lot of leverage to reduce the calibration overhead for different couplers, different interaction zones. So that's something to think about. And remember, this dashed line here that you see in the spider plot is Gidney's 2025, in some sense, state of the art. So getting better than that across all metrics is actually very encouraging. And this to us feels like having interconnects across different modalities would have very huge impact in this era. The last slide I would highlight is that because we have an end-to-end compilation, we can actually do resource estimation, not just of qubits and wall clock time, but actually give you what is the error budget? Where are we losing fidelity for these circuits as we grow in size? So on the left side, you see that typically if you just have a homogeneous system, your primary source of error is just idling on QPU actually, because like many of these algorithms, in Shor's algorithm, your qubit is idling for 97% of the time. So you're just wasting time doing cycles, doing quantum memory experiments there. But if you use heterogeneity, you actually can bridge that gap. And then the last part is you can ask the question, what happens if atoms become faster? It actually further helps with the state transfer rate and things like that. So with that, thank you for your attention.
Thank you. Oh, okay, first I was too quiet, now I'm too loud. Thank you. I think we're running slightly over time, so we don't have time for questions. Well, thank you again. Our next speaker is Erika Magnusson. She's going to speak about multi-reference error mitigation for quantum computation of chemistry.
Okay, and this is actually grand.
Please take it away.
Yes. Okay, so now for something completely different then. So I will talk about reference state error mitigation, and I'm from the chemistry department, so it's more of a chemistry-inspired thing. So what is reference state error mitigation? Well, I have a little blurb here that's a chemically inspired error mitigation technique with low cost for near-term quantum computation. The core idea then is that we have a desired state, say a ground state that we want to compute, and then we have a reference state that we approximate the noise of the desired state by. So what then is a reference state? Well, it's an approximate solution that is somehow cheap to classically obtain. So here's a little sketch of like how this works. We have here some kind of observable expectation value. And then in theta here is some kind of abstract parameter space. In blue, we have the exact behavior, which, no noise then. And we have 2 points marked out. We have the diamond, which is the, say, ground state then, the state we want to find. And that's the lowest in this case. And then the round is a reference state. Oh, that is somewhat close. So if we add noise, now I have written VQE, but this could in theory be anything. We, of course, get worse results. And also we can see that the diamond might shift, so maybe the true parameters is not what we actually got. However, we know exactly where the reference state is, so we can actually quantify exactly how wrong were we. And then what we do is that we simply subtract how wrong we were. So it's a very simple idea. And what do we need to do this? Well, in theory, it could be used with any method, like here it says VQE, but you can do anything. And also you can do it with any observable. And of course, we can combine this with other mitigation strategies like readout or so on. And to do this, all we need to do is just to measure this reference state. Let's see if I can, this thing. And well, the drawback, of course, is that as a very simple subtraction, we can, of course, overshoot, and it is not variational. So then what defines a reference state or a good reference state? Well, first off, we need to be able to get both of these points. So we need to be able to prepare it on the quantum computer, the green point, and we need to be able to actually get the true answer here in blue. And then, of course, we need it to be a somewhat good description of what we want to describe in the first place. So it needs to be reasonably close. So now we will just briefly talk about the actual problem, which we are handling in the rest of the presentation, which is the electronic structure problem for quantum chemistry. And I will just be extremely brief here, but it's basically we have a fixed molecule, like the nuclei are fixed and the electrons can move however they want. We want to find the ground state, so the lowest energy state. And the big problem is that every electron repels like every other electron. So that's called electron correlation, and that's what we want to solve with the quantum computer. And starting point for the quantum computer calculation is something called the Hartree-Fock solution, which is completely uncorrelated, so the electrons don't feel each other at all. And we could use this as our first reference state to see what happens. So here we have some results from actual quantum computers, and it's two very simple molecules. It's well, hydrogen and a helium hydride ion. Let's begin by looking at the black thing. So the FCI, that means full configuration interaction. And that is equivalent to doing an exact diagonalization of the Hamiltonian you have encoded on the quantum computer. So that is the true answer we asked. No, the true answer to the question we asked to the quantum computer. But this is not actually the true answer in reality, because then we would need infinitely many basis functions, so infinitely many qubits, which is a bit tough. Then in yellow, we have the VQE results, so the quantum computer algorithm, also with readout error mitigation. And then in orange, we get with the Hartree-Fock reference subtracted. So then we can see that we actually get quite close everywhere. And then in particular over here, this is close to the actual bonding region of the molecule. By the way, this is in like distance. We stretch the hydrogen. And the energy is in Hartree, which is about 27 electron volts. And yeah, we see, of course, here it was best, and here it is not as good anymore. And this is because in this region, the chemist will be able to tell you the electron correlation is more important, essentially. And here for helium hydride, meanwhile, it's more equal because it is not as correlated. And we also see that we can overshoot indeed. So here we are actually going too far. And okay, so this worked quite well for the non-correlated stuff, the weakly correlated molecules. But what about the more strong correlated problems? That's the ones we want to tackle in the first place. Well, I said Hartree-Fock is not inherently not correlated, so we would want to extend this to correlated reference states, what we call multi-reference states. And there's many different ways you could go about doing this, but our approach is based on state preparation. So we add a little state preparation block to our quantum circuit. And this is this blue block then. And the key ingredient here is these G, the Givens rotations, which is they rotate amplitude from one qubit to another. And with this kind of layout, we can prepare an arbitrary state. But because we are extending the circuit, we don't want to make too big of a state preparation block. Therefore, like the source of these multi-reference states that we have here will be truncated states from various chemical methods. So here we see a symmetrical stretching of a water molecule. And in the close to the bonding region, it is not a very correlated problem. But as we stretch, it becomes quite correlated. And we see that with the Hartree-Fock reference, we are way off. So how does it work when we add the MR state block? We get this blue here. And let's begin by the light blue. So that is just before the mitigation itself. And then we have just extended the circuit. And all we have done then is incur extra noise. So we are performing worse. But after the actual mitigation, we are performing better everywhere. And then in particular over here, where we expected more electron correlation. Then we will move on to molecules that are actually correlated in their ground states, like F2. And F2 is quite nice because we can describe it quite well with a very short reference state. So then we didn't even incur any extra noise. We have actually just converged better everywhere. And then in particular here around 1.5 Ångström, because here we didn't converge in the first place. So we are actually reaping some state preparation benefits as well. And after the mitigation, of course, we are quite well everywhere. This is within like 10 to the minus 3 Hartree, which is a kind of measuring stick that we go for. And then N2, however, is a different story. This is a bit of a tougher case. And here the extra stuff we have added have completely destroyed like the shape of our curve here. It has been flattened out, which that's not good. But after the actual mitigation procedure, not only do we actually outperform like the Hartree-Fock reference, but we actually get like closer everywhere and we get the shape back, which is very nice. So to, well, conclude, it's the reference error mitigation strategy is as good as your reference. So if you have some problem where you have a classical reference, this might be for you. And yeah, here's some of the other people who have worked on this and the 2 papers on this.
Thank you. We do have time for questions. Yes.
And was it real quantum computations or it was simulations on some nice model?
The first one was with a real quantum computer, and that was the one that had reference, readout mitigation as well. But the later examples were simulated with noise model, so it's both.
Over there.
Yeah, thanks for the talk. So I have a question. I mean, you are only using this readout error mitigation. So I mean, do you think, I mean, if you use like GNE or even this probabilistic error cancellation method, the result will improve for the quantum chemistry problem? Because the kind of plots that you have shown, I mean, the classical result is known, like for complicated molecules, maybe where you don't know, then how will you scale, right? I mean, how will you subtract the noise?
Sorry, I didn't get quite the question.
Yeah, my question is like for more complicated molecules where you don't have the classical solutions, how do you
Okay, yeah, no, so the thing is we don't need like the exact solution, because then of course that would be the best reference because then you can subtract all noise, but it's enough with a solution. So we have quite a lot of methods to get some kind of solution in chemistry. Like, for example, now I didn't really point it out in the presentation, but all of these reference states are from completely different sources. Like this is from couple cluster, this is from configuration interaction, and this is from DMRG, for example. So you can kind of just go.
All right, thank you. Our next speaker is Johannes Heinzhoff from IQM. He's going to speak about error correction experiments on cloud quantum computers. Please.
Hello, thank you, Simone, for the introduction. My name is Johannes Heinzhoff, and I have an honor to represent the quantum error correction experiment efforts at IQM. I have a pleasure to work with a lot of really smart engineers. More than 150 people have contributed to the setup, software, and the theory used for our experiments. Especially, I want to highlight the members of the quantum error correction teams, Florian Vignot, former member Jakub Rožek, Oleksiy Fedorets, Panu Vesanainen, and Zorav Majumder. At IQM, we build hardware. We develop two different architectures. Square arrays of qubits are well established, and surface and color codes have been demonstrated before. At IQM, we also develop a constellation architecture to enable even more different codes. In the constellation architecture, we introduce a computational resonator which enhances the local coupling, and this allows us in error correction enables us to make stabilizers with a higher weight, longer spatial reach, and also spatial overlap, which enables new codes. And the connectivity can be slightly more enhanced by adding some long-range couplers. So it's just a modest amount, one coupler for every second qubit. And all these couplers are parallel, so we don't need to cross. And we also do not need periodic boundaries. We can use open boundaries. And on such architecture, we can measure so-called barbell stabilizers. And if we tile some part of the plane with these barbell stabilizers, we can implement QLDCP codes, which are, for example, 7 times more qubit efficient compared to surface code. So I think that these are the best codes for superconducting architecture. We have already demonstrated quantum error correction experiments on a small unit cell published in PRX Quantum, and the description of the barbell code is available on arXiv since June. But today I actually want to talk about experiments which you can immediately do on the already available hardware over IQM cloud platform, IQM Resonance, where we give access to 16, 20, and 54 qubit devices. And today I want to talk about the 54 qubit device. So the first thing we can do, we can easily place a distance-free surface code patch on a subset of the 54 qubits using only 17 qubits. And in these experiments, we use standard CSS surface code, and we do not have a reset integrated and also no leakage reduction, but we use leakage removal by post-selection. And in a memory experiment, we prepare one of the 4 logical states, 0, +, 1, or minus, and measure the fidelity as a function of number of QEC cycles. And we see an exponential decay, and we can extract the decay constant. So we observe now 1.8% error per cycle, which is the best batch we have done so far. In this hero batch, I want to highlight that the worst 2-qubit gate in this batch, so you cannot see the mouse, but on the top of the blue curve, which is the distribution of 2-qubit gate errors, you can see that the worst 2-qubit gate is 98% fidelity. And this turns out to be quite important. We can compare the performance of this batch to another one, highlighted by purple color, which will make use of one of the couplers, which on this device is really bad. From these distribution curves for this patch, you can see that the worst 2-qubit gate has less than 90% fidelity. And this has a dramatic effect on the error rate. So compared to the 1.8 we got for the best patch, this worst patch gives 5.3% logical error rate per cycle. And the lesson I want to share with you is that it is really not sufficient to compare the median values of the errors highlighted by the gray dashed lines, because for these two patches, these median values are almost the same, but the worst qubits really have a huge effect on the performance. Now I'll enable the laser pointer, so these are the worst qubits I'm talking about. Over here, the blue line goes too far to the right. And of course, there are methods to mitigate and address that in future, but so far we have not implemented any of these mitigation strategies. Instead, we have characterized 4 different distance-free patches, so it would cover the whole emerald device. And by comparing the logical error rate, it is clear that the purple patch is a clear outlier. It is clearly the worst performing distance-free patch. And now we compare this to a distance 5 patch, which makes use of all the good and bad qubits. And from the comparison of the logical error rate, we can see that the error suppression factor is slightly below 1, so we are not yet at the error correction threshold. But I'm quite sure that if you would fix this coupler, we would be there. So we are quite close. We haven't fixed the coupler yet, but we can share some tricks we had to do to get to this performance. And these tricks are already described in the supplementary materials of prior works, but I think they are not sufficiently appreciated by the community who are not the experimentalists, but the users of the cloud access quantum computers. So something experimentalists definitely wants is a precise control over timing of the pulses. For example, if one wants to align a dynamical decoupling window indicated by the orange color exactly into the middle of the C0 sequence, or do a subset of the measurement operation to be covered by the dynamical decoupling window. To have a precise control, one needs to go beyond what is available in gate level access. The experimentalist also wants to have a more precise control over which operations happens at the same time. For example, in the gate level access, the duration of the measurement operation is as long as the slowest component. So in order for the measurement, the digitizer, which acquires the analog signal, takes the most time. But this should not prevent us from starting the next quantum error correction cycle as soon as we have stopped driving a readout resonator. And this simple trick already saves us considerable amount of error correction cycle duration, which reduces the effect of the non-coherent errors. And all such small tricks are necessary to get to good performance. Another distinction, which maybe is not sufficiently appreciated, is that there are different types of readout. In the end of the quantum circuit, one should use a readout which is optimized for the maximum state assignment probability or highest readout fidelity. But in the middle of the QEC, you want to use mid-circuit readout, which is optimized actually for quantum non-demolitionness in the case you do not use reset. We define QND-ness by the strength of the local correlations in the long chain of readouts. It is the math behind this method is described in our recent work in BRX Quantum. And pulse level access also gives the user soft information. So before the digitizer discriminates the signals into zeros and ones, one can, in pulse level access, we provide to the users in-phase and quadrature signal amplitudes, which allows one to do more careful decoding, which takes into account the confidence in the result, or enables leakage diagnosis or boss selection by recognizing also the F-state occupation of the qubits. So by using these tricks and other similar tricks, over last year we have improved the error rate of the distance-free patches on our existing hardware by an order of magnitude, and hopefully we continue this trend later this year and into 2027. So later this year we will deliver to our customers already 150 qubit devices, and hopefully we will be these devices will be below threshold and enable quite a big set of different quantum error correction experiments. And I wanted to stress that for these results, it is important to use pulse level access, because this unlocks better performance, and this is already available on IQM Resonance today. And I hope that IQM Resonance could serve as a reference platform for the community, such that it would be possible to make apples-to-apples comparisons of different strategies on the same hardware. So I think it is something which could be valuable, because not everyone has 8 cryostats in a basement and their own clean room. So having access to pulse level access to cloud quantum computers, I believe will be very useful for the community. And with that, I thank you for your attention. And
thanks. We'll take questions. Over there.
Thank you for the great talk. It was nice hearing about your strides towards getting below threshold. My question for you would be, have you ever tried looking into adaptive syndrome extraction? Because now you have this concatenated architecture, right, between in this barbell code thing?
There was a key part of the question I did not hear well. Have we considered what?
Adaptive syndrome extraction. Have you heard about this?
Which kind of syndrome extraction?
Okay, so this is a proposal by Norbert Husen from the Gottesman group, where they basically say if you have these concatenated code structures, right, you have the small code and you have the larger barbell codes, that you only run the small stabilizers and do syndrome extraction of the larger stabilizers only if you see an error on the small structures.
Yeah, so as I understand the question is if you have already considered code concatenation, and today the hardware is small, so we build hardware and we have to make research which is relevant for the near-term hardware. So when you start bottom up, it makes sense to like we focus on things which are for the realistic hardware size. So later code concatenation definitely becomes relevant, but first we have to engineer good like low-level codes, and later this can be concatenated with another code level. So this will come later.
Let's take one more question over there. Leo, please.
Thank you. Amazing progress. Could you comment perhaps on the performance without leakage post-selection?
Yeah, so I'm sorry I don't have a backup slide for that, but if we do not use leakage post-selection, it adds about a percentage point to each of these error rates today. And we are working on integrating a leakage reduction unit into the cycle. Thank you for the question.
Let's thank Johannes again.
Thank you. Thank you. Hi, everyone. My name is Archibald. I work for Riverlane. I am a quantum scientist. And today I'm going to be talking to you about directional codes. This is some work that was a collaboration with 2 of my co-authors from Riverlane, Georgie and David. Georgie was leading the project. And this is a paper that we published about a year ago and substantially revised about a month ago. So if you already know the paper, then you might be interested in the revision. It finds new code instances, better ones. It compares against the Tory codes, uses a fair decoder for all codes. And so this paper is a code construction, so a quantum error correcting code construction, and of a new family. And the motivation behind this is this tension that exists between wanting a simple QPU connectivity and wanting efficient quantum error correcting codes. Simple QPU connectivity is preferred because to avoid the additional engineering challenges and for scaling to be easier, as well as having lower physical error rates. And you want efficient quantum error correcting codes because that means that you can pack up more logical information for a given number of physical qubits. So there are two kind of like archetypical examples of kind of that represent this tension between the two. There's first the surface code that requires degree 4 connectivity, planar architecture, but is not very efficient. What this means is that for a target number of logical qubits and target distance of your code, you will need a lot of physical qubits, relatively speaking. On the other side, another good archetype is the bivariate bicycle codes. Those are much more efficient. The main downside, a big downside is that it requires degree 6 connectivity, which can be implemented using square grids, and additionally 2 long-range couplers per qubit on your grid. What this allows to do is that now each ancilla qubit is connected to a much more non-local qubits, which means it can measure out stabilizers that are much more non-local, and you have access to codes that are a lot more efficient. So the question this poses is whether it's possible to have a code that has actually both advantages, that is both efficient and also has low connectivity requirements. So directional codes shows that this is indeed possible, that you can go a bit beyond your connectivity constraints. The philosophy behind it is that instead of finding a very efficient quantum error correcting codes and then finding a syndrome extraction circuit that meets a certain connectivity that you want, here we reverse the problem where we generate a method that generates syndrome extraction circuits that by design already meet your connectivity, and then we do a numerical search to find whether there exists good and efficient codes. So the gate that is at the center of this is the ISWAP gate. It's the gate that we use for syndrome extraction circuits. It is special because it both entangles and moves the 2 qubits that it involves. It's natural to use it for superconducting devices because it's been natively demonstrated before, and it's been demonstrated to perform well. It can really be thought of as being a CX and then a swap, or a CZ and then a swap, up to single qubit Clifford gates. And because of this equivalence, we will actually, in our construction, be using CX swap and CZ swap instead of ISWAP. But at any moment during the construction, we can insert an ISWAP and single qubit Cliffords instead of those to have a circuit that's exactly logically equivalent and requires exactly the same connectivity. So for construction, we start with a checkerboard pattern of data and ancilla qubits. Each ancilla qubit is connected to 4 data qubits that are its nearest neighbors. Now imagine that you apply a layer of those control parallel swap gates, and you apply it between each ancilla qubit and the data qubit that lies north of it, and you make that choice for every single qubit. So you have a tiling like this. The effect of this layer is that first you have, for every single ancilla qubit, there's a syndrome extraction effect, that is the control parallel part, that entangles it with the qubits. And there's additionally a swapping effect. That means that all of your ancilla qubits will move up by 1 unit, and all of your data qubits will move down by 1 unit. Effectively, what this means is that each of your ancilla qubits is now connected to 3 new data qubits that it wasn't connected to before, and this is the case for every single ancilla qubit. And another feature that's nice is that the effect on the global layout is that you recover again a checkerboard pattern, which is a fresh slate from which you can apply another one of these kinds of layer. So here we made the choice of north, but really there are 4 different layers like this that you can choose per direction: north, east, south, west, where the name indicates the direction in which all of the ancilla qubits move. So those are going to form the building blocks of our syndrome extraction circuits. So if we start with the X basis resets on ancilla qubits and end with X basis measurements on the ancilla qubits, then we can insert in the middle some sequence of those directional layers. And that can be a sequence of arbitrary weight, arbitrary length. And the number of directional layers that we insert here will be exactly equal to the weight of the stabilizers that we'll measure out. So here we still only require square grid connectivity, but we're actually moving our ancilla qubits around so we can actually measure much higher weight stabilizers. So a good example of that is this N2, E3, N2, so north twice, east 3 times, north twice, where you can see here that those sort of snake-like shapes, those are stabilizers, and the circled qubits are the ancilla qubits that are responsible for measuring at those stabilizers. You can see that as the syndrome extraction circuit occurs, they move to become direct neighbor with each one of the qubits that support their stabilizer. And you can see that you go much beyond the square grid connectivity, but you are still restricted to square grid connectivity. So with this idea, we actually perform. Oh, sorry. How do I go back? Oh yeah. So with this idea, we'd actually perform a numerical search over possible sequences, and then we need to put those stabilizers and those circuits and those qubits onto a torus to give it a finite number of physical qubits. The particular torus that we choose determines the number of logical qubits and the number and the distance of the code. So here, this is 2 examples for the same sequence, for the N2, E3, N2 sequence. So here it's wrapped around a diamond-shaped torus, and here around a rectangular torus. Different parallelograms. So the way that it's defined is that it's defined by a parallelogram, and you identify opposite sides, and that gives you a torus. And so different tori give you widely different number of logical qubits for the same code, and number and distance. So with this, so we only did a numerical search up to weight 7 stabilizers, just to have sort of a proof of concept. And what we found for the best sequence and the best parallelograms, like torus that we found for this, is that it significantly outperforms the tori code, which is the rotated tori code, which is the best code on that same topology. Here, this is a graph of our results. On the y-axis, you have the logical error rates, and on the x-axis, the total number of physical qubits. You can see that the directional code lines lie much lower than the tori codes and surface code lines. And this is a quantum memory simulation where we use circuit level noise. We decode it with tesseract over d rounds of syndrome extraction. Overall, the footprint that you gain is that you only need 1/3 to 1/4 of the number of physical qubits of the tori code to reach the same number of logical qubits and the same logical error rate. So to summarize, we showed a new family of quantum error correcting codes. It's both CSS and QLDPC. It leverages the ISWAP gate to only require square grid, sometimes hexagonal grid connectivity, depending on the sequence, but measure very much longer stabilizers. It outperforms the tori code and the surface code under circuit level distance. Note that about 2 months ago, there's been 2 works that have extended this to planar connectivity. So that have taken the same idea and added boundaries to it and showed that there exist instances that actually perform well. And that outperform the surface code. So those are Vine code and directional tile codes. Thank you.
Thank you, and we have time for questions.
Hi, thank you for the great talk. I wanted to ask about the coders. You said you decoded that with Tesseract. So I know from experience Tesseract was really, really slow.
Yeah.
So do you have any sort of idea of like what kind of decoder would you need for this? Like how would you progress with the decoder here?
Yeah, so yeah, Tesseract is very slow. The idea with using Tesseract is that it's a very accurate decoder. So you can kind of get an approximation of kind of the best decoding performance that you can hope to achieve if you have a dedicated decoder that is both accurate and fast for that particular code, so that you have a fair comparison across like Tori code, directional codes, and all the ones we compare. We don't know of a decoder like this for now. It's an open question. Those are not graph-like decoding graph, so you can't just use like minimum weight perfect matching. But yeah, it would be nice to find one.
Was there one more question over there?
Thank you. It's a very nice talk. So to me, it looks like the directional code is more like a trading off with more time, like running time compared to other surface code, like so that you can have a better logical code error, these things. So what do you think that the qubit coherence requirement for this code is more like, things like it be double or 4 times order for the required qubit coherence other than compared to other codes? It's like that.
So are you asking whether these codes are trading space for time compared to the Tori code? Is this correct?
Yes. Yes.
So in a way, you're right, they are, but they do still perform better even though they do this trade-off. You can see this because here we do our quantum memory over d rounds of syndrome extraction. And here really we like this shows the footprint improvement despite the fact that your syndrome extraction circuits are a lot deeper and that you still do d rounds of syndrome extraction. You can still see that there's a real gain, and so it's not just like you converting space for time. It's really you have a real improvement in like the logical error rates, and yeah, the footprint that you would need to achieve a given logical qubits and LER.
All right. Thank you again.
Thank you.
Our next speaker is Ilan Rosen from IBM. He's been on stage before. And please take it away.
Great, thank you. Great, yeah, so I'm speaking today from IBM Research. I'm speaking on behalf of my colleague, Ali Reza, who couldn't be here today. And I want to talk about a recent paper that he and several other of my colleagues recently put out. And this paper is about sort of a subtlety in how to learn noise on quantum computers. But let me actually start by backing up and just trying to talk about error mitigation in the first place. Why should you use error mitigation? What can it do for you? So, okay, noise in quantum computers. I think you all know a lot about this, probably a lot more than you want to. And this isn't going away anytime soon, unfortunately. And of course, what does this do to actual programs that we run on computers? Well, we get the wrong result. We get a biased result, right? So in short, what is error mitigation? It's just a way to recover something that either is the right result or hopefully a lot closer to it, okay? So the idea of error mitigation is, first of all, this only works on expectation value problems, right? But that's a lot of our workflows. And there's a little bit of overhead. So the cost you're paying for error mitigation is you need to take more samples. You need to run more circuits on your quantum computer. But what do you get back? Well, you get back a better result. And it works shockingly well, in fact. So, you know, it's not a free lunch, but it's something that we use in almost everything we do at IBM. And I do want to say, you know, this isn't the cheat. So first of all, this doesn't replace good hardware. You need great hardware to do error mitigation, and error mitigation makes it even better, right? And the second thing is this is not a replacement for error correction. In fact, it's complementary to error correction. We think that you know, at least in the near future, the first error corrected devices are going to need error mitigation to get high quality results. But the other thing is that error mitigation works now, right? We don't have to wait. Good. So error mitigation comes in essentially two flavors. Okay, so the first is error extrapolation-based techniques. So the idea here is to say, what is noise exactly doing to my result? One way to do that is to just turn up the noise. So intentionally amplify the noise, watch how the result changes, and then just try to look back and figure out, well, if I had zero noise, what would the result actually be? The second flavor are cancellation-based techniques. Okay, so these are techniques where you learn something about the noise, and then you figure out how to invert that noise effectively on the quantum computer, and then you can sort of directly measure what is effectively the zero noise result. So the former class of methods are heuristic methods. These are methods in general that don't provide some guarantee that there's no bias in the mitigated result. But again, they work shockingly well in a lot of cases. They certainly get you closer to the unbiased result than you would have otherwise. The second class of methods, these cancellation-based methods, these can actually provide a rigorous guarantee. So a rigorously unbiased result. Now the key though, for many of these techniques, they rely on a noise model. We have to know what noise looks like on the device, and for the error mitigation to be reliable, that noise model needs to be representative of the device. Okay, and so obtaining these representative noise models, that's what I want to talk about today. Good, so let's actually zoom in on probabilistic error cancellation, which is essentially the gold standard of cancellation-based error mitigation. So PEC works in sort of three stages. The first is to condition the noise. So we need to make the noise a little bit better behave, something that we can characterize easily and manipulate, work with mathematically easily. Once the noise is conditioned on the device, then we can go ahead and characterize the noise, figure out exactly what it looks like, build that into a model, and then we can invert the noise. Okay, so let's talk about those three stages. Okay, so conditioning noises, first of all, we're going to make a very general assumption, which is basically that everything you do on a quantum computer could in principle be noisy. That includes state preparation, measurement, and of course all the gates. Now what we want to do is polytwirl the gates. So polytwirling means adding single qubit gates randomly and averaging over many instances of these single qubit gates, kind of surrounding all the 2 qubit gates. And what this does is it converts noise, which in general can be very complex in quantum computers. It converts that noise to a polychannel. And polychannels are much easier to work with mathematically. In particular, we're going to make an assumption that the twirled noise looks like what's called a sparse poly-Lindblad noise. And what does this do? It lets us have this decomposition of noise. So basically what we can do is we can take the full noise channel, we can decompose it into a sum over many generators, and those generators are local, so adjacent qubits, and low weight, okay, the poly matrices. And then all we need to do is to specify sort of the eigenvalues of these generators, the poly fidelities, and then we'll have a full picture of our noise model now. Okay, so how are we going to do that? How are we going to find these poly fidelities? So the conventional picture for noise learning is the following. It's to sort of split the task into 2 steps, one for state preparation and measurement, and the second to characterize the gates, right? So this kind of works in the obvious way. You prepare 0 and 1, you measure 0 and 1, you check the fidelity, and then you start adding gates and seeing how that fidelity drops. That gives you the gate error, right? Now, there's a subtlety here, and you might have already seen it coming. So let's say I'm doing a state preparation measurement. Well, let's say I see some error, right, in the signal I get back. Well, did that error happen during state preparation, or did it happen during measurement? I actually don't know. And it turns out that's not because I messed up in this protocol, it's fundamental. And it turns out it's actually a gauge degree of freedom in the noise model. So these are fundamentally unlearnable parameters of the noise model. So the key result in this work by Ali Reza and my other colleagues is that it turns out the mitigated result doesn't depend on the gauge of the noise model. So the gauge is a physical thing in some sense, right? Quantum computers, it's definite whether the error actually happened during state preparation or measurement, and I can never learn that, but it doesn't matter. I will always get the right mitigated result, no matter what gauge my noise model is in. So that's the key result. The important thing is just that the noise model that I generate is consistent about what gauge it is in. Okay, and now we have our problem with conventional learning. It turns out that when we split the noise learning process between state preparation and measurement and gates, it turns out that those noise channels can be characterized in different gauges. And so what my colleagues have done is introduced a gauge consistent way of learning noise. And I don't want to go into too much detail today, but in brief, what this does is the key for the experts is to add odd depth circuits in the design matrix. So this is essentially an adaptation of gate set tomography. Two sparse poly-Lindblad noise. GST, of course, it's not efficient. It's been done maybe 2-3 qubits at most. This works for hundreds of qubits. It's very efficient. And it's also for the experts, again, if you know the ACEs framework, it's sort of a similar noise characterization process. Okay, one more key result though, is even though the mitigated result is independent of the gauge, it turns out that the path to getting that result is not. It turns out that different gauges, you have to pay different penalties in samples to do PEC. But they all give you the same result. And so one of the really cool tricks is you can just choose whichever gauge gives you the best result, right? So you can learn a model in one gauge and then just mathematically figure out an optimal gauge and do PEC in that gauge. And all of a sudden, for free, you're getting a much faster time to result. So let's look at an experiment by several of my colleagues. So what they did, they looked at a 20 by 20 non-Clifford circuit, and they measured a whole bunch of local Z operators. And okay, so this is a small circuit. There's an exact known theoretical result. And they did the unmitigated circuit. They got something kind of close. Great. Let's use gauge inconsistent PEC. Do we get a better result? Yes, we do, but it's still not perfect. Okay, so let's try adding gauge consistent PEC. And now all of a sudden you see there's these giant error bars, right? That's the sampling overhead I'm talking about, right? But if we go to the optimal gauge, this whole process becomes much more efficient. That's going to drop down the error bars. And now all of a sudden we have high accuracy result with very tight error bars. And these error bars start to become rigorous as we build trust in the noise model. So let me conclude with that. So the key is, look, error mitigation just works. It makes results better. And there's this subtlety about error mitigation, these gauge degrees of freedom, and this is something we can take advantage of and get a faster time to result when we're doing PEC. So I'm providing links here to some tools in Qiskit that are actually built to help you along this error mitigation process. And then on the right, of course, to the paper that I'm discussing today. And let me just end by saying, what if you want to do this yourself? Come talk to us at the IBM booth. We have programs available to help you get onto our devices and run your circuits, do these error mitigations. Thank you for your time.
Thank you. We'll take questions. Over here.
Thank you for this talk. How do your PEC deal with non-massive noise? How do the PEC deal with the non-massive noise?
Great question. Yeah, so that's a subtlety, a difficult subtlety of PEC. So non-Markovian errors are out of model. That is to say, PEC can't handle non-Markovian errors, and that's a similar statement to other forms of error detection and error correction, right? And so the key is for us to reduce the occurrence of non-Markovian errors in the first place. And to be frank, that's on us. So that's something we have to do at a hardware level. I talked a little about this yesterday, and you can look in our paper for some of our techniques. But yes, unfortunately, they are out of model for PEC, and by being really careful in how we calibrate our devices, what we can do is reduce those non-Markovian errors, sometimes at the cost of a little bit more Markovian error, but that's fine because error mitigation will handle that Markovian error.
I'll take my chance to ask my question of the session. It's from the very beginning. You mentioned that error mitigation and error correction, actually, they will go hand in hand. And if you could expand a little bit, is it going to be at the layer of improving the error correction gain or sitting on top of the error correction layer?
Yeah,
from a non-specialist, if you could take that.
Absolutely. So I'm afraid I can't give you a perfect answer because I'm no expert in this. But you know, we've seen error correction experiments around the world, and they're absolutely heroic experiments. And the best devices right now are getting slightly above threshold. And we know that asymptotically we'll get exponential improvement, but it's going to be a while until that exponential improvement really looks like there's no errors happening. That's true fault tolerance, and we're not going to have that for a while, I don't think. So in the meantime, we'll have logical error rates that are dropping by orders of magnitude here and there, but errors still happen and errors still bias results. And so what you can do is just right now, we encode logical information, one logical qubit, one physical qubit, right? And we error mitigate on that logical qubit, which is one physical qubit, right? But you can do the same thing if your logical qubit is an error-corrected qubit comprising physical qubits. The circuits look the same.
All right, so the mitigation layer sits on top of the correction layer.
Exactly.
Okay, thank you. Maybe one quick question if there is. Otherwise, we'll thank the speaker again. And proceed with the very last talk of this session. So coffee break is approaching, but not there yet. Visma Yoshi is the next speaker. Please take it away.
Hello everyone, I'm Vismay. I'm from IIT Madras. Today I'll be speaking about how we can implement noise-adapted quantum error correction on superconducting quantum processors. So conventional QEC schemes, they are agnostic to the device hardware noise. What we mean by noise adapted is that we have some knowledge about the structure of the noise and we are exploiting it to correct for the device hardware noise much more efficiently, primarily being able to reduce the qubit overhead a bit. Transmon systems basically are typically modeled as a Jaynes-Cummings model, as a Jaynes-Cummings Hamiltonian, and when we trace out the cavity, we are left with the T1 and T5 noise. The dominant microscopic noise mechanisms are T1 and T5. So I'll try to address these two noises using quantum error correction and error suppression techniques. I'll also show you some results where we have implemented a protocol on the IBM Torino machine. I believe it's a 133 qubit machine. I'll talk about what I mean by post-selected QC scheme because this is slightly different. But yeah, so I'll be introducing a new measure to faithfully benchmark our QC protocol. So let's look at the device noise. So as I said, the quantum error channels are the amplitude damping channel and the pure dephasing channel. They are represented by the Krauss operators A and E, the set of Krauss operators A and E. And gamma and P are the amplitude damping and the dephasing noise strengths. A0 is our no damping event Krauss operator, and A1 is our damping event Krauss operator. All my previous speakers have spoken about big codes. I'll be talking about a small code. I'll be talking about a 3-qubit permutation invariant code, which perfectly corrects for amplitude damping noise. There is a caveat. I'll talk about it. So the 0L is just a 3-qubit W state. The 1L is the all 1 state. We assume that the noise is independent and identically distributed, so it can be written as a tensor product. The picture shows basically the code words in the green subspace. The red boxes, the red ellipses show the action of the Krauss operators on the code space, and we can see that it's orthogonal, so we can distinguish it very nicely. So our code words have odd parity, and our noisy subspace has even parity. So to distinguish these two subspaces, we measure the Z1, Z2, Z3 stabilizer using a syndrome qubit. The +1 outcome corresponds to the single damping event. The -1 corresponds to the no damping event. The recovery Krauss operators here are R0 and R1. And one glance at it will tell you that the recovery is non-unitary and trace decreasing, which inherently makes it probabilistic. So we need to post-select the successful outcomes at the end, which adds to the overhead over here. We measure the performance of a protocol using the state fidelity, where curly is our error channel, curly R is our recovery channel. And the reason why we are choosing this code is because the worst case fidelity, the worst case state fidelity is much better than the 5-qubit and the 4-qubit codes, which are previously known. So the 3-qubit code is the smallest code for perfectly correcting amplitude damping. So how do we implement a non-unitary? So we just do a polar decomposition of the recovery R. And we just embed the square root R dagger R into a larger unitary. Basically, we block encode it. And as you can see in the circuit, we get a final output as a ket-Scheil tensor ket0 plus ket-Scheil tensor ket1n. And when we measure the extra qubit in the Z basis, the +1 outcome corresponds to a successful implementation of the recovery. And the worst case probability of success is 1 minus gamma the whole square. Coming to a schematic of the protocol, we have a multi-QEC scheme. We have 5 qubits, 3 data qubits, and 2 ancilla. The 3 data qubits are first encoded, and we allow a free evolution of the qubits, and where no artificial noise is injected. And then the top qubit basically helps us perform the syndrome measurement, and then we apply our recovery. The bottom qubit allows us to do the block encoding of the recovery, and we measure it, and we store the value to post-select the successful instances. And then we reset our syndrome and the block encoded qubit, and we repeat it many times. Then we decode it, and then we measure the state fidelity. So for the circuit design process, we are not using the exact recovery, because using the exact recovery requires, I think, around 500 to 600 CZ gates. But we did a low noise approximation where we set the recovery strength to 0. So experimentally, it's much easier. You don't have to set the recovery noise strength every single cycle. So it brought down the CZ count to, I think, around 36 or 35. And the good thing is that we are still able to correct for all the first order AD noise. And then we just input it into an ansatz, similar to what Erica showed previously. And then we use a Frobenius norm as a cost function, and we get our circuit decompositions. Coming to the results, before that, this is our IBM Torino layout. We chose 3 sets of logical qubits. So we demonstrated 3 logical qubits simultaneously. These 3 sets were chosen because the data qubits have similar T1. They are around 200 microseconds. So the hardware results are as follows. So the gray dots basically show the average T1 of the data qubits. The background represents the maximum and minimum of that set of data qubits. The green dots represent the performance of the 0L. The blue dots represent the performance of the 1L. The 30 microseconds represents the maximum total free evolution time, the delay block, which we had seen in the protocol. Yeah, and our QEC cycle is pretty fast. It's around 3 microseconds, and we were able to improve the T1 from 220 microseconds to 720 microseconds on an average. Moving on, so I'll be combining the QEC scheme with the dynamical decoupling so that we can also correct for the dephasing noise. If you still remember the code words are immune to the dephasing noise. But if we choose a superposition state like a ket plus logical state, dephasing noise will act on it. And other than dephasing noise, we'll also face some crosstalk, which is effectively a ZZ interaction. And the dynamical decoupling sequence of our choice is chromatic Hadamard dynamical decoupling. It's a very recent scheme by Professor Daniel Lida's group. They call it CHAD. And the dynamical decoupling sequence is applied only during the free evolution period of the data qubits and the ancillary qubits. So again, coming back to the Torino layout, our system qubits comprise of the data and ancillary qubits. Our spectator qubits are the nearest neighbor to that set. I mean, we can also apply the DD on the full 133 qubit machine, but it suffices to just apply the DD on the nearest neighbor qubits. These are the hardware results for the ket plus logical. We can see the maroon line, the maroon data, where the DD is not applied. We see the characteristic ZZ oscillations. But in the orange data points where we have included the dynamical decoupling sequence, we were able to mitigate these harmful crosstalk noise, and we were able to protect our logical plus L state. And the DD also helped us to improve our T2 lifetimes. And one thing to note is that our QEC is only able to correct for the T1 noise and not the dephasing noise. So the fidelity drops to 0.5 pretty quickly, but it's still much better than the bare qubit. And yeah, so addressing the elephant in the room, this is a probability of success. It's very bad. The green ones represent for the ket 0L, and the blue curve represents the probability of success for the ket 1L. So we wanted to come up with a measure which could incorporate the fidelity and the probability of success in a way that it gives you a faithful comparison, because it's not fair. So how do we do that? We defined a gain measure for it. So our gain measure is just the ratio of the SNR, the signal to noise ratio of the QEC scheme, to the SNR of the bare qubit T1 scheme. Experimentally, we calculate the SNR similar to the multi-shot approaches seen in other experiments. And theoretically, we are calculating our SNR by assuming an underlying binomial distribution. And since a scheme is post-selected, it's limited by the measurement readout noise. So in our model, in our very simple model, we have just included the average measurement error. In much more complicated models, you can include the gate noise too. And yeah, this is the gain from a protocol. Our very simple model is able to capture the trend of the maxima gain, but we still require much more points, which is difficult on a public hardware because we already used like I think 1 million shots, which is a lot. So for all the data points, so getting even more data points is very tough on IBM. Which is not possible because there's some drift noise and other sources of noise.
Hate to interrupt, but we should slowly wrap up.
Yeah. I'm done basically. Sorry. And yeah, our worst case performances for 1L, and we are currently at that star point, and we hope that to see some appreciable gain, probably somewhere around 10⁻⁴ error is required to see improvement to IR protocol. So yeah, basically we were able to show our protocol demonstrate logical T1 enhancement. And one thing which we would like to incorporate is use FPGAs to terminate in real time the unsuccessful instances. And this is our team. And yeah, thank you for.
Thank you so much. So I'll take this chance to thank all the speakers of this session again, which is now over. We have coffee break until 11:30. So thank you all. All right. Oh, great.
Hello, everyone. My name is Michaela, and I'm excited to chair this next session. And we're going to start out with an invited talk by Antti Vepselainen on implementing and characterizing high-fidelity gates in the IQM quantum processors. So let's welcome Antti on the stage.
All right. Hello, everybody, and good afternoon. My name is Antti Vepselainen, and I work at IQM as a head of QPU performance. So today I'm going to talk about our work on implementing and characterizing high-fidelity operations on our quantum processors. You can see there are a lot of people have been involved in this work, so many thanks to all of those people who have made this possible. So at IQM, we develop quantum processors using Transmon architecture. So over the years, we started like in 2022 with small 5-qubit processors that were in planar. And over the years, we've increased the number of qubits. And that's mostly been enabled by more sophisticated 3D integration techniques. And later this year, we will be releasing our 150-qubit processor, which includes, among other things, 3D integration, forcing-on routing. So that's our path for scaling up. In addition to this kind of planar or superconducting qubit grid processors, we are developing architectures with higher connectivity to enable our error correction roadmap. Johannes in a previous session mentioned some of those architectural choices we have and motivation. But in this kind of talk, I'm going to focus on our grid-based QPUs. When the size of these processors increases, like there are more and more qubits, it becomes more and more important to also focus on the performance of those processors. We need high fidelity operations and improving calibration techniques to enable us to run algorithms on those systems. So in this talk, I'm going to focus on our efforts in calibrating such processors, and in particular in characterization and optimizing the processor structures. First, I'm going to talk about our results on small test devices, and then later on I will show how some of those results scale to larger systems. All right, so the workhorse in our processors is this kind of a small unit cell where we have 2 qubits connected by the tunable coupler, which enables us to turn on the interaction between the qubits. So we have basically, by changing the frequency of the coupler, we can find a coupling off point where the qubits don't interact, and then we can change the coupler frequency to enable interaction between the qubits, and this is how we do our 2-qubit gates. One thing I need to know though is that at this off point, the ZZ interaction goes to 0, but there's still some remaining XY interaction in the systems, and that XY interaction causes wave function hybridization between these 2 qubits. And this basically raises the question of what is the optimal value for these couplings between the qubits and the coupler. Because on the other hand, increasing the coupling enables you to do faster 2-qubit gates. The interaction strength grows and you get better gates. But at the same time, the hybridization between the qubits also increases, causing errors in simultaneous single-qubit gates. So somewhere here in the middle, there's an optimal value for this coupling. And in our work, we first performed the simulation, trying to capture this trade-off between the high coupling and fast qubit gates, and slow coupling and high fidelity single-qubit gates. And we chose some parameter somewhere here in the middle, an optimal value around 60 megahertz. That should give a good compromise between these two operations. In order to verify that this choice is correct, we fabricated a device with ideal optimal coupling and with a goal of being able to implement high fidelity operations for single-qubit gates, 2-qubit gates, and the readout in the same device. Our goal was to reach 3.9 fidelities for all of these operations in the same device. In the literature, there have been several demonstrations for high fidelity operations of these individual operations on different devices. But this time we want to put them all of those together in a single device to verify that this kind of structure, coupling structure we've been studying is capable of providing high fidelities also in larger processors. So here you can see an image of an older generation of the device, but the new generation device looks quite similar in most of these features. In particular, this is a kind of a platform where we can characterize and study the fundamental physics of these quantum operations, in particular with the focus on leakage, which is going to be very important to suppress for error correction applications. So just to go through a little bit like what kind of error channels we have in these kind of devices, starting from single qubit gates, we know that the main error channel comes from the leakage to second excited state. And then we have the quantum crosstalk caused by this hyperstation I mentioned earlier. In larger devices, we also need to take care about microwave crosstalk, which becomes worse and worse like the more qubits you have in your system, and it's this kind of impact from all of the qubits in the system are going to cause you trouble. In 2-qubit gates, we have a little more complicated energy structure, and thus we have much more different kinds of leakage and error channels, which we need to count one by one. In particular, we are interested in ISWAP errors, leakage to coupler, and leakage to second excited state. Now, in addition to the leakage to the coupler that causes errors, we also have this problem of coupler excitations Alba talked about yesterday. So those coupler excitations can be caused by the leakage process or any other mechanism like such as thermal heating of the coupler. In larger systems, we need to also account for spectator errors. And of course, for readout, we care about the relaxation during the readout, and then there's leakage processes. All of these missed problems we know about. It's important for us to be able to characterize and know about those. In larger systems, readout-induced crosstalk is very important. So let's start by looking at how we calibrate those 2-qubit gates and how we can use that kind of knowledge to understand how to characterize the system. So we basically, if you look at the standard ZZ gate, which we do is a diabatic version of the ZZ gate, we apply 2 pulses, one to the qubit, another one to the coupler, which allows us to tune on the 2-0 state of the qubit to be resonance and 1-1 state of the qubits, which causes then accumulation of conditional phase. And while we at the same time we need to minimize the leakage to 2-0 state at the end of the process. Typically, this kind of a gate is calibrated by sweeping, for example, the maximum frequency of the coupler, and then the qubit frequency during the gate gives you this 2D landscape. And then you have 2 conditions you need to satisfy at the same time, which gives you basically requires you have 2 experiments, 2 conditions, you can find an optimum from this plot. But this is actually not a very accurate way of calibrating your gate. You can see that it's like the visibility of what's the actual right point in this plot is quite weak. So in order to calibrate a high fidelity gate, we need to do something more. So next, I will show a little bit about our application or our work on implementing error amplification applications that allow us to detect and minimize the leakage errors to second excited state with much higher accuracy than by just using this simple experiment. So the standard way of doing error amplification, people have been doing this for years, is to just prepare, for example, the 1-1 state, and then you apply the ZZ gate multiple times, and you look at the population, the second excited state. And then you can sweep one of your control parameter, in this case, coupler flux amplitude, and then you will see this kind of a plot here over here with where you can identify a minimum point. It's this kind of smeared out white area in the plot. But it's actually also from this plot, it's surprisingly hard to find the minimum. Like you can visually see that there are, you can start to see the small oscillations when you go a little bit away, but this white area is still quite blurred. And the reason for this existence of this blurring is that in addition to our small parameter which we want to detect, which is this leakage, small leakage, the second excited state, we also have Z rotations in the 1120 subspace. And the Z rotation actually is effectively an off-resonant Rabi process, which results in you, when you error amplify, instead of going to 2-0 state when you have multiple gates, you do this small rotation around 1-1 state, and you have very, very low visibility. So one way to fix this problem is to apply additional single qubit gates interleaved with every CZ gate in this kind of process. So this idea is very similar to what MEAD by Google Quantum AI has. And the purpose of these small single qubit gates here is to actually amplify the rotation at every step. So instead of doing a very small leakage to second excited state with every gate, you actually, every time you do this gate, you do almost a full pi rotation from 1,1 to 2,0 plus the additional small amount of additional leakage. This makes the Z rotation actually to be very small compared to the full rotation you want to detect. And this helps a lot. Now, there is still one problem. It's possible to have destructive interference in this kind of process. So even though you would do this kind of amplification, you can have such a phase for this pi pulses that it cancels the signal you want to detect every time. So what we've added is to run randomization over the phase of these pi pulses for every step of the process. So every time we repeat this experiment, we choose a different phase for the pi pulses. And as a result, you can see that now we have very, very good visibility. The rotations in the 1120 subspace is very, very strong. We go all the way to second excited state, and even this, like when we sweep the Kappa flux amplitude, we can see that there's a very, very distinct peak, which we can use as a calibration for the calibration very easily. Over the years, people have developed a zoo of different kinds of experiments for error amplification. So here is a standard experiment. Then there's a delay protocol, which actually tries to achieve a very similar thing by adding a delay gate after every CZ gate. There you can get a very good visibility, but you need to calibrate the exact value of the delay, and it's different for every Kappa flux amplitude. So it takes quite a lot of time and effort to implement this kind of protocol. There's a FLOK-A calibration by Google Quantum AI, the MEAD protocol, which we couldn't run in our processors. And then finally, we have the PALEA, the method we've developed, which contains the intrinsic randomization over phase, and thus is very efficient for calibration needs. So you can see this is the main workhorse we use for our calibrations. Now that we have some efficient error amplification experiments, we can proceed with a gate calibration procedure. So here you can see a typical gate calibration experiment where we sweep the Kappa flux pulse duration, and for each of these points, we recalibrate the gate and then use the error amplification to detect any leakage processes. And you can see that, okay, there are some variations. But we can find a point where the leakage to second excited state of both of the qubits is very low. Additionally, we can use PALEA for detecting ISWAP errors. So we just change this, the initial state slightly, and that allows us a very, very accurate measurement of the ISWAP errors. And we can find out that they do change when we change the Kappa flux pulse amplitude, but there are a lot of values which give a very low ISWAP error rate of 10 to minus 5, around 10 to minus 5. We can verify also that we get a low leakage to coupler by using the delay protocol, and we can find out that roughly, independent of the Kappa flux pulse amplitude we choose, we get 10 to minus 4 leakage to coupler. Okay, so now that we know how to calibrate our gate, we are ready to proceed with benchmarking the gate, and that we do typically with the interleaved iterated RB experiment, so where we just interleave multiple CZ gates with this Clifford sequence. And in this case, we get a pretty nice fidelity. When we interleave one CZ gate, we get fidelity of roughly 99.94, which is pretty good. And when we add more CZ gates, the fidelity starts to drop a little bit. This is a nice experiment because it's sensitive to both coherent and incoherent errors. So instead of just randomizing over coherent errors, when we interleave more and more CZ gates, we can get a little bit of sensitivity if we have calibration errors in the system. So here you can see how the ZZ error, or how the error changes as a function of number of CZ gates we interleave with the gate. And we find a peak fidelity of 99.95 in this experiment if you use all of these kind of data points to fit the gate. Okay, so that's pretty good. We can also repeat this benchmarking protocol over 40 hours, and we can then calculate an averaged gate fidelity of more than 99.93, around 99.94 for this period of time. And we don't get any gates that would be below 3 nines. So okay, that's pretty good. we're quite happy about this. In order to really understand where these errors come from, we can form an error budget for this gate. So the incoherent errors we can get mostly by just, instead of interleaving a CZ gate, we interleave a small delay that corresponds to the duration of the CZ gate. This gives us an estimate of like what's the T1 and T2 contribution of the qubits themselves to the gate error, gives 4 in minus 10, 4 to 10 to minus 4. We can couplers also have their own coherence time. So when we do the gate, we bring the couplers closer to the qubits, which causes some extra, potentially some extra losses due to the lower coupler coherence. But we find out that together, the qubit coherence and the coupler coherence roughly corresponds to 6 to 10 to minus 4. Then we have the leakage to the second excited state. This is a small contribution here. And then we have some accounted for coherent errors, which are typically like some calibration errors or non-idealities in the system, which we could not suppress. And then we have the small contributions from the ISWAP errors and then the coupler leakage in addition to this. Okay, so that was the CZ gates. I think it's pretty nice. Now we understand like where our errors come from our CZ gates. So let's move to the single qubit gates. So as mentioned earlier, the main limitation for single qubit gates in our system come from coherence of the system, but also from this hybridization errors. So when, because through the wave function overlap between the qubits, there is the simultaneous gates might suffer. So we basically what we do, we move the qubits away from each other and idle them roughly so that they are at half of their unharmonicity. This allows us to avoid the leakage to second higher excited states in addition to the 0, 1, 1, 0 errors we would get. We can also do more advanced pulse shaping to further suppress these errors. But here in this work, we just focus on this simple system. So this data is from a different device. So now we can like just run a benchmark on this device we were originally studying, and we can find a pretty nice single qubit gate, simultaneous single qubit gate fidelity of 1.5, 10 to minus 4, and then very low leakage. We use purity randomized benchmarking to detect the leakage, where we have modified it slightly to also measure the F-state population during the benchmarking, and that gives us here, basically in this small plot, you can see this change in the second excited state population. It's a very small change, indicating very low leakage. So we're pretty happy we can make single qubit gates to be high fidelity and low leakage. Finally, we have readout. So in order to suppress the decay during the readout, we use solving technique. It's been studied by several people already earlier. But this allows us to get a pretty nice fidelity above 99.94 for both of the qubits. So, okay, now we can do a very good assignment of our states. Of course, if you want to do mid-circuit measurements, which would need for QC, this might not be the best strategy because you still have some additional leakage to excited state. You can see it here in this plot where we can distinguish two different blobs. One of them corresponds to G state, and the other huge plot corresponds to F state. And then there's just a little bit of stuff in the E state. And then when we apply the final pi/2 gate, everything that's now in the E state in the self readout will correspond to leakage after the readout. Okay, so this is small non-ideality, but this is perfect for these applications and to do it in the end of the gate. Okay, so then we take all of these error mechanisms together, and we can roughly compare errors in different gates to each other, and we very naively just sum them up, which is we get 99.8% fidelity. Maybe not the right thing, not the most exact thing to do, because in many applications you have different numbers of these different gates, so you have different prefactors here. But it gives an idea that, okay, this device works pretty well. Now I would jump directly on my last slide, which is about scaling to larger systems. So now that we developed these kind of small, or like these error amplification techniques and all the other small techniques to suppress errors, we've moved on, we implement them in a larger system, in 54 qubit system, and we can see that these techniques have significantly reduced error rates, and we can now reach 99.6% median CZ fidelity in a 50 qubit system. And all of these improvements together, they allow us to now entangle all the qubits in this processor. So we have a benchmark for the Z and Z state fidelity. We can see that for all the 54 qubits, with some readout error mitigation, we stay above the 0.5 fidelity. So I think that's pretty cool. Even without any readout error mitigation post-selection, we can get the fidelity above 0.5 for 40 qubits. Okay, so it's a pretty cool device. And this now brings me to my conclusion slide. So I would especially want to thank these people who have provided most of the data shown in this talk, and of course the whole IQM team who have made this work possible.
Thank you, Antti, for a very nice talk. We have time for one quick question. Yes, I see one over there.
Thank you for a very nice talk. So I have a two-part question. One is when you do the error budgeting, how do you account the leakage in the coupler? Because what I see is like you are taking the second population of the qubits, not the leakage in the coupler. And second part was that in yesterday's talk, we saw that around 40 millikelvin of the coupler temperature. One of the talks from your company said like it's the thermal population of the coupler will prohibit from getting higher fidelities, and you still got 99.93. So do you have any say on that?
Yeah, so we have pretty low qubit, like pretty low temperatures in our processors. So the thermal population of the couplers are very low, which is compatible with this kind of result. The other aspect, of course, we have leakage to coupler, but this leakage during the process is actually accounted by the IRP fidelity. So there is a small amount of coupler population initially in the beginning of the process in the coupler. That is not visible. It's very low though. But then this basically, the leakage is included in all of this.
Let's thank Antti again. I'm very excited for our next speaker, which is Johan Bock-Severen from Morten Kjærgaard's lab in Copenhagen, and he will talk about superconducting qubit Lindblad dynamical models via gradient optimization. Let's welcome Johan.
Amazing. Thank you, Michaela. I am Johan. I'm a PhD student in Morten Kjærgaard's group Squid Lab at the University of Copenhagen. And today I'll talk about how we model our quantum processor in our lab. So we have this device made here at Chalmers, which we are very happy with. It's been a real workhorse for us. And what we want to do is we want to make sure that we can model it to the best of our ability or any dynamics that go on this device. So usually we would start up with what we intended to have when we started up with local Hamiltonians and nearest neighbor couplings. And then in addition, we'll have local decays like T1 decays, T2 decays that affect our dynamics. In principle, if we have these things, we can simulate the dynamics that go on a device by calculating it in the Lindblad master equation, here with a Hamiltonian term describing the unitary dynamics and a part describing the dissipation. Now, in reality, as we've seen throughout this days, there are much more that can go on a device. Namely, we can have spurious two-body, three-body interactions, we can have higher level systems, or maybe defects as well. And in addition to this, we can also use our creativity and figure out what would the impact be of correlated decays in our processor as well. And today I'll go through how we intend to figure out which parts of this model is necessary to model some sort of dynamics. And we'll focus mainly on the spurious two-body, three-body interactions and correlated decays. So I'll do this through 3 steps. The 2 first will be on idle dynamics, talking how we can scale Lindblad dynamics to work on the whole 5-qubit device. And I'll talk about how we select an adequate model for describing the full dynamics. And I'll give a quick highlight of how we use this to study more interesting dynamics like time-dependent envelopes or non-Markovianity, for example, through a coupler. So let's start with the basics, and recapping state tomography and building towards Lindblad tomography. So when we have a quantum state, we cannot simply just measure its state. We have to probe it multiple times through a lot of different axes to fully reconstruct what the state of the quantum system was. So for these 3 qubits, we'll have to do 27 different basis measurements to reconstruct the full density matrix. And that we do by figuring out which density matrix was the most likely to provide the data that we were looking for. Now this exponential scaling really starts to hurt fast, and just going to 5 qubits will end up having 243 different basis measurements in order to fully reconstruct the 5 qubit density matrix, which also is quite significantly larger with 32 times 32. This is of course just a state, and we want to move towards something that a process that happens on the processor. So let's start with the static process tomography, and here we'll, instead of looking at just a state, we'll both need an input and a mapping to the corresponding output state. So we'll now, instead of just doing basis measurements, we'll also have to loop over all the initial states, giving us a much larger exponential, here where we need 4 to the n different input states and 3 to the n different output states. So for 2 qubits, this is still feasible, and we can do the input polys and the output polys and map them with a poly transfer matrix like this. But now going to 5 qubits, it really starts to hurt. Now the number of configurations that we have to do would be 250,000, and the parameters that we would have to include in our poly transfer matrix would be 1,000 times 1,000, around 1 million parameters. Things become even worse when we want to talk about dynamics, because now we don't want to talk about just one process, but a whole family of processes which takes an initial state into another state a time t later. So in this work, we will assume that we have a Markovian map, namely that we can describe it by defining a Lindblad generator that we can exponentiate to give us the map to any time. Now we'll perform the process tomography with one key difference, and that is that we'll stop at a few times t to make sure that we get time-dependent statistics as well. We'll do this for 30 time steps, giving us a total of 7.5 million different configurations to map, and we'll get a dataset that looks like this, where we have the time of the x-axis, we have the occurrence of some example bit strings along the y-axis, and then we'll have all the configurations stacked like this. Now, to make sure we can fit this, we developed a framework which uses gradient optimization, and I'll just highlight or quickly go through how it works here, but I would love to talk more about it if any of you want later. In a sense, we choose some parameterization of our Lindblad, which we then solve with an ordinary differential equation solver. Then we'll calculate what was the likelihood of our data given that model, and we'll make sure that everything is differentiable such that we can go backwards again to calculate the gradient of our parameters or with respect to our likelihood. If we loop over this a couple of times, then we'll have gotten a full model of our system or set of parameters, and we can extract the Hamiltonian, the Lindblad jump operators, our initial state, and etc. from our state. But most importantly, we'll get the likelihood of this model family, and that we'll use to select the adequate model. So let's go on and decide on how we find the adequate model. So we can just choose maybe a general model, but for a 5 qubit system, this would correspond to finding 1 million parameters, which would be a general Hamilton and a general jump operator formalism. Instead, what we're going to do is that we are going to make some sort of structure, and we'll here expand our Hamilton and our jump operator in the number of qubits, having an interaction graph that goes from simple on the left to much more complicated on the right. We'll now define some models here, and these models will correspond to where we cut off the desired expansion. So we can have a model like the one we described before with nearest neighbors here, or we can make a more complicated model here, for example, with an all-to-all connectivity of our qubits, or all-pair connectivity. This will give us 2 models. We'll have model A and a larger model, model B. And of course, model B is larger, so it will fit our data better. But by how much is what we want to determine. So let's see here, model A is nested in model B, where model B just has expanded parameters. And what we can use now is use a well-tested statistical framework from the 30s called Wilks' theorem. And this, for us, this means that the model B will perform better, or if model A is true, then model B will perform better with a relation that depends on the number of parameters that we added. And what we can do is now we can check how much did model B break this assumption? How much extra explanatory power did it provide? So now let's combine it all together. What we're going to do is we're going to make this grid going from local and no dynamics to local to free local. And we're going to do it for both the Hamiltonian and the dissipator and arrange them in a grid like this. We'll now perform our Lindblad tomography analysis. We'll take our data and then we'll start fitting. And we're going to do it in the lower left corner, where we're going to have just no dynamics at all, just a steady state. So this is of course not a good model, but we can expand it in two different axes by adding local Hamiltonians or local dissipation, and this will give us two contributions. We now choose the one that has the most explanatory power and then go this way. We can then continue with this as we increase the complexity of the model, and we follow this path from the least to the most complicated model. And what we want to highlight is when did the expansion of a model stop to provide any explanatory power for what we described. And here we see that we get explanatory power all the way through, also when adding two local dissipation and three local Hamiltonians, but we didn't get any explanatory power adding the very expensive free body dissipation terms. So we conclude that this three local Hamiltonian and two local dissipation model was adequate in describing our idle dynamics of our 5-qubit device. So before I end, I just want to highlight two additional results from this paper, and this is where things start to become a bit more interesting. Now we only talked about idling dynamics of our device, but we want to figure out what really contributes when we start to model some dynamics. So the first result is that we can describe in the same framework, because we use ordinary differential equations, we can simply add a time dependence to a Hamiltonian and have that supported by default. So here we are reconstructing a gate that we play on a pulse by truncating it a few times, and then we can reconstruct the Hamiltonian of the pulse throughout this gate sequence. Another thing we can do is we can look at the coupler dynamics. So here we'll start to have effects of some non-Markovian dynamics. We'll have a coupler which we cannot read out. But here we include it as a latent two-level system and check if it's required by the data. And here we see clearly that we have a an effective 2-qubit system is not enough to describe the effects that we see from this. But when we add an extra two-level system to our dynamics, the quality of our fit goes up dramatically, and we even need a free local interaction to describe the full dynamics that goes on here in this effective Pauli model. So this was all I had for you today. I want to say thanks to my group at SQA and QCP, and then Chalmers for the collaboration on this paper. And then I'll suggest that you read the paper or find me and discuss more if you're interested in this kind of work.
We do have time for questions. Don't be shy.
Can I ask a bit more about this slide where you selecting which terms to add? Because I kind of thought that the conclusion is going to be that you in fact only need the simplest dissipative stuff, because it was like 408 versus 407.9. For me, this seems like the same number. So.
Yeah. So part of the slide is that the data set is very large, and I could report. So the number of parameters live in thousands, and the decimals that I had corresponds to hundreds of thousands in the likelihood here. So you need to calculate this explanatory power to model how much per parameter. But I think we give it with a few more decimals in the supplementary in the paper. So it's just because we are very sensitive to even small adjustments by taking this large data set. Yeah.
More questions? I have one, or was there? Excellent.
Is there some way to quantify this explanatory power of the model?
If there's a way of quantifying it?
Yeah, like giving some like procedural meaning to understand how much it helps you.
Yes, so I think my intuition usually comes from taking like symbol fits and the chi-square. So if you have Gaussian errors, it reduces to checking the reduced chi-square and calculating the p-value from this. So the intuition would be that every time you add one parameter, the likelihood should go down with 1 or 2, I think is the right normalization. And then you can calculate it from there. And then I would just say that it's a general way of checking whether added parameters to your polynomial fit would do any good.
I have one more question, because you have now a nice unit cell that you looked at, right? But I'm wondering, is it necessary or like feasible to go to larger scale processors? Or if it's fine just to really look at the smallest building block that you will use in your larger scale architecture?
Yeah, so we are thinking a lot about this as well. And the hope was that somehow we would converge in this group, because then we can start to think about where do we need to be sensitive in order to probe things more. So if we don't look for local dynamics, then we don't have to probe all the samples to be sensitive to it. So we can instead focus on smaller number of samples and, for example, reduce the number of jump operators that we have. And then it should be able to go on. But I think I would start with just doing a line and seeing how long interactions would be.
Excellent. Let's thank Johan again. Next up, we have my colleague Tom De Veer, who leads the research team at Quantum Machines, and he will talk about hybrid FPGA, classical fast feedback calibration of single and 2-qubit gates. Let's welcome Tom.
Hey, thank you, Michaela, and I'd like to thank the organizers. This has so far been a fantastic conference. So, as Michaela said, my name is Tom De Veer, and I'm from Quantum Machines. And I would like to talk to you about, indeed, this fast feedback calibration, but the context is drift mitigation. So how can we keep our quantum processors' control parameter at their calibrated value in real time? This work was done with Clemens and Jacques from Quantum Machines, and in collaboration with the team at Sandia National Lab. All the experiments were done at the Israeli Quantum Computing Center, and the QPUs are provided by Quantware and Colab. We start our discussion by noticing that parameters drift. So our qubits depends on flux and frequency, amplitudes, and all of them drift. For example, focusing on the material aspect, we have an example of squids that suffer frequency fluctuations, degrading both coherence, but also the 2-qubit gates. We know of a 2-level system that roam the frequency domain and hurt relaxation rates, and also hurt our error models, which are crucial for quantum error correction decoding. An example from our lab, we have frequency fluctuation, which is typical, happens sometimes between discrete levels in the span of less than a second. All of this needs to be calibrated in real time to ensure a smooth operation of a quantum machine. And the question of how to calibrate it depends crucially on where the information comes from. We have seen in the literature 2 major families of real-time calibration. On the left, this is a few papers from Google where they focus on calibration from syndrome measurements. So during the process of quantum error correction, we generate a lot of syndrome data, and we can ask how much error we have, or what is the syndrome error rate. This number is highly sensitive to how well we are calibrated. So we can inverse this process and calibrate our parameters based on minimization of the error rate. This was recently pushed to an edge, looking at the surface code, a huge surface code, and calibrating thousands of parameters simultaneously. So this work with no executional overhead over our quantum processors, but we rely on syndrome data. And syndrome data are not designed to calibrate. So they're not designed to answer any specific parameters. They're designed to help us with error correction. So the information per shot is very small, and we need to accumulate quite a few of them before we can make decisions. The other approach requires us taking parts of the system offline for a little while in order to calibrate them. For example, we can see on the left how a closed-loop frequency calibration allows to mitigate low-frequency drift. And in the right and the bottom, we see 2 figures which are basically unveiled in the last SQA conference, showing a Bayesian estimation of T1 measurements in a millisecond timescale, and even a complete calibration graph in the same timescale, where a dedicated FPGA protocol was used for every control parameter that needs to be calibrated. Looking forward, when we think about a quantum machine that needs to operate for long duration, we'll need both. And the question of which one to use depends on the availability and the precise context. In this work, we'll focus on the second family. Let's look at our protocol, fast feedback protocol. As an example, consider the problem of a pi/2 pulse. So we want to take our qubit from the ground state to the equator. We have to send some microwave pulse with some amplitude. If, as we have on the left, the amplitude is too little, we will under-rotate. If the amplitude is too large in the center, we will over-rotate. And if the amplitude is correct, as we see on the right, we will be roughly on the equator. Measuring this, even with a single shot, at least in the extreme cases, is pretty deterministic. If we under-rotate, we'll measure -1. If we over-rotate, we'll measure +1. In the center, it will be a coin flip, half-half. And this gives us an update rule. It's very simple. If we measure -1, we increase the amplitude. If we measure +1, we decrease the amplitude. That's it. Near the center, of course, we'll measure both, so we will deter, but the bias will drift us towards the correct value. By how much to change? This depends on a gain, which we can control, over a sensitivity, which asks how much we amplify our error. Let's say this in practice. This curve shows how the amplitude evolves with the repetition. Each repetition is a single shot measurement followed by an amplitude update of the protocol we just discussed. Yes, we start with a low value, we under-rotate, we measure -1, and the amplitude shoots up. After about 20 shots measurements, we are around our target, and now the results are mixed. It's plus, minus, and we begin to dither around the target. This dither is actually quite big, so we can help that by reducing the gain, reducing the step size. It helps. So now the dither is smaller, but at the cost of slower convergence. We can also increase the sensitivity here in orange. So now we amplify the error 5 times. We are more sensitive. And indeed, we converge faster with lesser dither, but at the cost of a lower tracking range. We have a risk of having an error in our calibration. The correct approach here is to combine all three. So we start usually with high gain and low repetitions, and when we go forward, we change it according to how we measure. This was so far calibration of a pi/2 amplitude. We need more than that in order to keep our qubit calibrated. We need all the qubit parameters calibrated, at least the drifting parameters. And we can do it with the same simple rule. So here you see 8 graphs that looks, except the readout one on the top left, pretty much the same. So we calibrate the bias, we calibrate the frequency, we calibrate the pi/2 and pi amplitudes, we calibrate the pulse amplitude to achieve the conditional CZ phase, and we calibrate the compensation phases for the target and control qubit in the case of a 2-qubit gates. It looks the same because it's pretty much the same. It's the same update rule. That means that we measure and we increase or decrease our control parameter based on our outcome. It doesn't take too long. Okay? If we look at the single qubit part of this graph, and this is a histogram of our measurements, looking at each protocol and how long it takes. So the single qubit part takes about 45 milliseconds, and the 2-qubit part takes about 40 milliseconds. So overall under 100 milliseconds. Now let's discuss drift, which is our main topic. Drift means that our control parameters change. So our goal is not to calibrate our parameter once and then let it move. We want to calibrate it when we go on with some other protocol, some other algorithm or state that we want to stabilize. And in this case, we want to stabilize the 00 plus 11 Bell state. So we begin with a baseline, and the procedure is simple. We change our flux with small steps. We change the flux. It's a 2-qubit system, so we change the flux of the 2 qubits in small steps. And we measure a tomography. The flux has some trajectory that you can see here. We have 2 qubits, so we have 2 curves, one for the control qubit, one for the target qubits. They drift up and down randomly, and the resulting density matrix on the right is a mess. It's definitely what we want. So now we interleave it. So the protocol now is to change the flux a little bit and then throw in 3 calibration shots. 1 calibration shot for the amplitude, 1 calibration shot for the phase of the control qubit, and 1 calibration shot for the phase of the target qubit, and then run a few tomography shots of our Bell states. We do it over and over again over the course, in this case, of 10 seconds, and the resulting density matrix that you can see on the right looks good. Okay? So it works in stabilizing the Bell state. And the reason, if you can see carefully, is as follows. So you can see the blue curve. This is our CZ amplitude and how it changes with time. And it correlates quite well with the red curve, which is the flux of our control qubit. This also unveils what is our sensitivity in this system. This brings my talk to an end, so I'll just quickly summarize. What I've shown you is that we can use a simple update rule that we implement directly on FPGA, and it's cheap to implement, that says that we have some measurement protocol that needs to be monotonic, and we can update our some control parameter in every step. And using this method, we can calibrate a variety of control parameters. It doesn't take too long. And if we interleave it with some other protocols, it allows us to stabilize some states. In this case, it's a Bell state, but it's general. Before ending, I would like to invite you to our workshop in which you can actually play with such parameters. So there are a variety of fast calibration protocols that you can run on FPGA, the Bayesian examples that we have seen before, and such examples that we have seen here. So come and play with it, bring your laptops, because you will connect directly to the Israeli Quantum Computing Center and run experiments on qubits. You can also come to our booth and do the same or discuss to us. Thank you very much.
We have time for a few questions.
Hi, thanks for the talk. You mentioned that there are two parameters, a gain and a sensitivity, but why is it not like G by S as a single parameter that you're adjusting?
Yes, thank you. So this is indeed the equation you see on the top of every slide here. They serve two different roles. So the sensitivity is actually not something we choose directly. So this is related to the error amplification that we have. And the gain is an arbitrary parameter that you can think about it as how much we want to average. So how many shots we kind of keep in our memory. So high gain means that we basically forget any but the last few shots, and low gain means that we remember for a long time. So those two parameters serve different roles. In the update rule, they come as just one number, the fraction between them, but underneath they serve different purposes and they act differently.
We have one more question up there.
Hi, thanks for very nice results. I want to ask, so you put like, so the drifts happen in millisecond scale, and you can also, like with your FPGA, can recalibrate the processor really fast. But can we recalibrate when we are running a surface error correction, or can we do this recalibration when we are running an error correction cycle?
Yes, thanks again for this excellent talk. Quantum error correction contains multiple areas. So the area that usually we talk about is the data area. So this is an area in which we want to preserve quantum information for a long time, and we run quantum error correction cycles over and over again. This area, in principle, we cannot touch. Okay? So there we have to rely on syndromes. I put an asterisk here because in principle you can, because we can move the information aside and bring it back, but let's put it aside. But there are many more areas. So consider magic factories, for example, magic state factories, or even bus lines. So these are surfaces that are just sitting there waiting for you to do something. And that's the majority of the area of a surface code machine. So all of these areas are available for calibration the way you like. And for the data, you can move it around. So I think that a full quantum machine will have to combine both methods. So calibrate on syndrome data when you have it, and when you can afford it, calibrate directly.
Excellent. Let's thank Tom again. Our next speaker is Jesus Jimenez Rodriguez from
Luciano Pereira.
Oh, Luciano Pereira. From ICFO, and he will talk about rigorous time-dependent Hamiltonian learning via continuous weak measurements.
Hello, yes, it's working, perfect. Yes, my name is Luciano Pereira. I am postdoc researcher in the Institute of Photonic Science in Barcelona, Spain. And today I am very happy to have the opportunity to share this work with you about Hamiltonian learning with continuous measurements. So, learning a Hamiltonian is a fundamental task for characterization and benchmark of quantum technologies. You can think, for example, in a quantum simulator, digital or analog. there are devices created to implement a particular evolution. So with Hamiltonian learning, we can test the quality of this implementation, for example. So Hamiltonian learning have been widely studied in the recent years for the time-independent case. We have many protocols that scale to large devices thanks to exploit the connectivity of the Hamiltonians. And also we have a lot of theoretical works to calculate the precision of these protocols. However, we don't have to forget that the real hardware is time-dependent. We have seen many examples in the conference, yes. We have shaped pulses or tunable couplers, yes. So we need time-dependent Hamiltonian learning to characterize these kind of devices. And this is a case that has been barely studied. And the few cases that we have now, most of them are heuristics, so they don't have like a strong theoretical background. So we want to try to fill this spot in the literature. So, well, we want to characterize time-dependent Hamiltonian. So we need first a way to extract information. So we use continuous weak measurements. This is basically the opposite to a strong measurement. Here we obtain partial information from the state, but also the state after the measurement is also like partially collapsed, partially projected into the measurement basis. This kind of measurement can be described by with this kind of master equation where we have basically I don't know if you see the pointer or whatever. You have this decoherence term. It's an effective effect due to the measurements. If you are measuring in sigma c, this is basically a dephasing. So yes, you have like a balance. You can use weak measurement to extract information, but you have a back action due to that dephasing. So any protocol have to work faster than the decoherence time. That's very important. So this kind of measurement have been used to perform Hamiltonian learning in superconducting circuit in a small scale, only for 1 and 2. Okay, so this said us two things. The first one is that yes, weak measurement can be implemented in superconducting circuits and with very standard tools. Here is the simplest example with dispersive readout. It's the standard scenario. But if we instead to use like a strong readout pulse, if we use a weak readout pulse, we basically implement a weak continuous measurement of the qubit. The second thing is a question: how we can scale the reconstruction beyond 2 qubits? Well, we have to like take the example from the time-independent case. They exploit the structure of the Hamiltonian. So our protocol, like this is like the target of our protocol, sparse Hamiltonians. So we have, or consider a Hamiltonian in the Pauli basis. Here the mu are the parameters, so it's the object that we want to estimate. We define this interaction graph, which each node is each Pauli term or represent each parameter, and the edge are basically, or they're connected if they share a qubit. And we define the degree of this graph as the number of connections, the maximum number of connections. If the degree doesn't scale with the number of qubits, we said that this Hamiltonian is sparse. So this is an example in a chain of qubits. So it's very important here, but I'm going to skip that for the time. So how we take this structure and exploit it for the reconstruction? Well, if we evaluate the Heisenberg equation for the evolution of the observable, of the continuous observable we are measuring with the weak measurement, we have this equation. This equation, in one side we have basically the derivative, in another side is the commutator. So here we have a matrix M, which depends of basically the Pauli terms from the Hamiltonian, the input state, and the continuous measurement. So it's something that we can calculate. We know that all that's objects. And also we have the parameters. So basically this is a linear equations for the parameters. So if we measure the left sides, we can invert and obtain the parameters. The problem that this could be a very large system of equations. So we notice that using the structure, again, the connectivity, we can reduce it into a set of smaller inversion problems, one for each side, for each qubit. So we pass from there to that system of equation. Basically, using the interaction graph, we can define these sets in the left, yeah, with different colors. So each set basically is a different system of equation. And here is very important that we can also demonstrate that the number of probes, that is the number of input steps that we need to realize this protocol, doesn't scale with the system size. It scales with this interaction graph. And here basically the demonstration of that. I'm going to pass here due to the time and go directly to the reconstruction protocol. So in the protocol, we have to measure, the first step, measure the signals over the time and perform the following loop. We have to know the state in the beginning at time 0. So I don't know, we performed state tomography before, or maybe we had a very good model of the input state. With those states, we construct in the step 2 the system of equations. We solve them in step 3. Then we assemble all the information in step 4 to reconstruct the Hamiltonian. And then we need the states. We have to know the state in the next time. So for that reason, we have to propagate the state by the master equation and the estimated state for this time. In this way, we have the state for the next time, and we can perform again the step about estimation. So basically, we have like two subroutines. We are alternating an estimation subroutine and a propagation subroutine. And this is very important. Because if we calculate the error depends on both. So this is the error of our method. We have here n the number of qubits, s is the number of input states. The capital N is the number of trajectories, the number of shots that you are repeated to estimate the observables. And sigma is the minimum singular value of the matrix that you have to invert. Depends on the input state. So you can see that we have two terms. One is the statistical one, which is basically the estimation, the error due to the estimation. And the second one is the bias. It's a deterministic bias due to the propagation. Here we consider Euler method for solving the master equation, the simplest one. So that equation, that part comes from the Euler method. So yes. And it's very interesting that both like pull in different directions. The estimation is divided by dt and another is multiplied by dt. So here again, we have like a balance. We have to try to optimize the error. So decreasing the time step implies that you need more trajectories to estimate the Hamiltonian with a particular quality. And with this result, we can state that sample complexity theorem. So basically, this only works when you are above, above this deterministic bias. And the number of shots that you need to obtain a estimation with error epsilon with a dt, with a time step dt, is that one. So you can see that it's not exponential with the number of qubits. It's linear in the number of qubits times the number of input states, the number of probes. Well, we did simulation to verify our results. So here you have a change of qubits, 6 qubits, some of the parameters. And you can see that the estimated signals are in great agreement with the theoretical signals, which is the solid blue line versus the dashed lines. Well, we also test what happened for large times, because due to the decoherence, we are losing information, so in some points we cannot reconstruct anymore. So we notice that our method is more like robust against that if you increase the number of input states. So here for 9 states, you in time 2.5, I don't know if you see it, the reconstruction and the theoretical signal split. But if we increase the number of input states, you have a great agreement for larger times. We also compare the sample complexity scaling. They are in great agreement with our theoretical bounds. And also we can see from the plot the effect of this deterministic bias due to the integration. So in the blue plot, you can see the standard shot noise, but for large budget of number of shots, you see the saturation, like a stagnation, I don't know, a plateau. Yeah, this is because we achieved that precision. So in order to obtain better precision, we had to reduce the DT, but also increase the number of shots, according to the theorem I showed before. So that is my talk. Some fast conclusions. Yeah, we propose basically a rigorous protocol for time-dependent Hamiltonian learning with continuous weak measurements. And it have a lot of very good properties, and we have several ways, several avenues for our research. So, well, that is. Thank you for your attention. Thank you for organizing for the opportunity, and thank you to my collaborators for the great job.
Thanks, Luciano. We have time for one quick question.
Thank you, Luciano, for this very nice talk. Can you comment on, I think it was preposition number 2. So basically it said that like, yeah, in here. So this kind of like bound of the error like goes with probability 1 minus delta, right?
Yes.
But when delta, the ideal case is that delta is very small because then it's probability 1.
Yeah, exactly.
But then inside the equation, we have this 1 minus delta. That means that the error will grow a lot, right?
Yes, exactly.
So, I don't know. Like,
yeah, this is
the sweet
basically
spot?
a confidence region. So yes, you have to set the delta, I don't know, to have a estimator with a confidence of 99%. So the point is, yes, that is dividend, but it's inside a logarithm. So even if delta is very small, the logarithm like doesn't permit this number to explode. So in general, it's not a problem. So yes, you can verify, put the numbers, and check how many trajectories do you need. Yes, in fact, it's also in the sample complexity. So in general, it's not a problem because it's inside the log.
Thank you.
Thanks, Luciano. We're moving now to integrated AI calibration with another speaker from IQM, Alejandro Gomez Friero. And yes, he will tell us about enhancing calibration and experimentation with agentic workflows.
Okay. Hi, everyone. First of all, I would like to thank all of my teammates for this work, and I will also have my disclaimer that AI tools have been used for making this talk, and it's important as a community to be transparent to create a trust as well. I would like to talk to you about some work that we've been doing in integrating AI tools for experimentation and calibration in general. Some justification about why we might want to do this. So in order to autonomously characterize QPUs, we have to, in general, expect the unexpected. So things like fabrication, for example, you end up having statistical variation in your chips that might even have some spatial dependencies, things like that. There might be new recipes that are being tested, and so there might be lots of issues depending on what's happening. When we're doing this design R&D, you might end up with chips that have new physics that we want to study. You might have different parameters, different priors for what we are measuring. There's also an issue that many people have been highlighting, which is that we might have incomplete models in our software stack, and we need to somehow also be able to actively take them into account. And of course, there's a typical hardware failures of some lines stop working, some modules randomly break. And if you're an experimentalist and you've never suffered from this, please raise your hand because it's the most common problem that can happen. But yeah, in general, at scale, not just in number of qubits, but also in number of chips, we have to deal with known unknowns and also unknown unknowns. And we have to deal with all sorts of failure modes. This is something that typically, for small chips, was done by an engineer. Have your Jupyter notebook open, execute some code, evaluate the images, and also evaluate some statistical metrics. and then do a human in the loop sort of a close experimentation. As we keep scaling up, this becomes very cumbersome, and so we have to start automating our process a bit more. At IQM, we define this graph-based calibration software, which allows us to, in general, add dependencies between different calibration tasks with some other nice features, such as being able to write specific fallbacks whenever a failure mode that we know of occurs and whenever we can detect it. This is something that, of course, if you want to talk about, please, catch one of our engineers at any point. How do we do with this? Well, we have, let's say that we have a Rabi node that executes a Rabi experiment, and because it's a new chip, we might end up in a situation where the priors that we selected for the search range are pretty bad. If we can detect that this has happened somehow, so again, statistical methods or however else we want to do it, then we can execute a fallback that retriggers the same experiment and modifies the search range accordingly. And of course, we can have more than one of these for the same node to deal with all of the disjoint sets of failure modes that we might find in a QPU. Ideally, we would like to have a full set being handled, so all possible failure modes that we have ideated or even not ideated being solved. And that's something that is now very much actively being done in the field through AI agents. This is a bit of a data mining project that I did for this talk. This is a amount of archive papers on quantum physics that either mention AI agents anywhere in the text or explicitly in the title or abstract of the paper. And as you can see here, this is a logarithmic scale. It's exponentially growing over the last few years. It's definitely one of the fastest moving fields right now. Soon, more than 5% of papers in the quantum physics archive might use AI at all. And the number of publications is doubling every few months. So it's getting harder and harder to keep up as well. So I think everyone has sort of seen this happen over time in all fields, not just quantum. I'd like to highlight some very important work that has happened in the last year and a half or so about this new field, which is self-driving laboratories for quantum. So the first work is the K-agents that was done in 2025, where they have a team of agents interpret a human natural language instruction and autonomously execute all sorts of experiments and interpret them and end up in a final result. Then there's the heuristic laboratory here, where they essentially combine a few AI agents with short and long-term memory, and they are able to autonomously reproduce papers from literature in an extremely short amount of time. And recently, a Chinese lab has managed to calibrate more than 100 qubits autonomously using their own fine-tuned small model by distilling human knowledge as reusable skills. So this tells that everyone is sort of looking into automating as many tasks as we can, because unfortunately we cannot have engineers 24/7 looking at data of hundreds and thousands of qubits. So what we would like to do right now is have a loop like this, where some experiment is executed, an agent in the loop interprets the results and produces some structure and unstructured object that tells it like, hey, this has obviously failed. And please correct it for me, and it will succeed and move on to the next task by itself. There's obviously like two challenges that come to mind immediately. First of all is, can an agent actually interpret these results as well as an expert can do it? And can we do it fast enough without breaking our bank? So the first one is, let's start with that. So we, together with NVIDIA and other collaborators from industry and academia, developed a benchmarking data set containing good and bad examples of calibration images across different modalities. You can find the paper in the QR code over there. And here are some results from both the Qwen 3.5 model and the NVIDIA Ising-1 model, which is fine-tuned from that one. And you can see that for all of the benchmarks, there's a considerable improvement on the zero-shot evaluation, which means that for each experiment, we don't provide an example image of what good or bad is. But unfortunately, it suffers from a in-context learning degradation, which means that if we were to showcase good or bad images of this specific experiment, actually the scores don't improve, which is non-ideal. Now, during the preparation of this talk, the good folks at NVIDIA actually made a new model, so I had to improvise this a bit. But this new model is based on the Gemma family of models from Google, and they actually managed to improve the in-context learning scores, and they also provide a quantized model that is smaller and faster while still keeping most of the gains from the fine-tuning. So yes, there are some models that are somewhat capable of interpreting calibration results, and it's a field that evolves not in years, but in months. Now, about the fast and cheap, this is our proposal of how we are integrating AI agents into our GBC calibration flow. Each of our nodes generates a number of images, say for a hypothetical case to have 100 qubits, that's 100 Rabi plots. We basically parallelize over our available nodes of replicas of the same visual agent. And we have a final review agent that is condensing all of this information into a final result that then automatically triggers whatever fallback is necessary. And our framework also right now is automatically passing all of the context that each of the agents requires. And everything is structured and transparent, and we can, always revise and improve over it. As an example, I made this demo a few months ago on our IQM Garnet chip, where I purposefully chose a bad configuration of the initial parameters to evaluate how the agents are capable to react in real time to all of the images. So here you can see some Rabi experiments that are suboptimal. The sweep range was wrongly chosen on purpose on a subset of them to see if you will be able to evaluate this and correct for it automatically. The agent decided to just rerun the experiment on the wrong subset of qubits. And then we continue. The same for a Ramsey experiment. It found one faulty Ramsey qubit autonomously. And again, re-executed with a different set of conditions. Then surprisingly, the single shot readout actually worked fairly fine. You don't need to correct anything at all. Then we do a round of error amplification where like a few of the qubits were also detected to be wrong and autonomously correct for that subset. And finally, everything is good and the chip calibration can continue. This is a bit of a demo flow, but I hope that it illustrates that indeed these medium-sized chips are already possible to automate in that regard. And that's all from me. Thank you so much for listening. Some tidbits is that agentic workflows and things like that are right now very, very interesting in our field. Our models are becoming really good really fast, and so we need ways to benchmark their capabilities. And consumer level hardware like the DGX Spark is already enough to do demonstrations like the one I showcase here. Thank you very much.
We have time for questions.
Thank you for the great talk. Can you elaborate on how you incorporate human domain knowledge with a general LLM?
Yeah, our current approach is that the agent is living in the same environment as our code base, and we provide automatically, for example, if we're running a certain node or experiment, we are passing the doc strings of our experiment, which contain the physics of the experiment and some other information about what the parameters do. And what also we dynamically give it what possible fallbacks it can trigger with all of the parameters it can touch.
One more quick question.
Hi, thanks for the nice talk. What was the difference between Visual Agent 1 and 2?
Yeah, one sec. Let me just quickly go back to, you mean this guy or the benchmarks?
Yeah, indeed, like in between these two
Yeah.
visual agents.
Yeah, so here basically, because we have a large number of qubits and we want to make this evaluation fast, we need to parallelize over replicas of the same agent. Otherwise, this will take hours if we do sequentially evaluate the images. And so imagine that we have one GPU hosting the first agent, another GPU hosting the second agent. We can send a few requests concurrently to the first one, a few requests in parallel concurrently to the second one. And so the actual visual evaluation of the whole set of images is essentially roughly constant time instead of linearly increasing with the number of qubits that you have.
I have a naive follow-up question to that because I'm wondering, why do I even need visual agents for all of the qubits?
Yeah. That's a great question, and it's kind of hard to answer. I would say that the indication right now is that visual agents are capable of interpreting a more continuous latent space of images instead of a discrete space of words, of token words and numbers, and also are able to see correlations between things like fits and data and stuff like that. So it's an open field of what's the best way to go about it. We believe that image evaluation is very promising right now. But for example, the Chinese lab actually did not evaluate images. It fine-tuned on traces of humans calibrating a quantum computer.
Fantastic. Thank you very much, Alejandro. We made it to our last talk of this session, and we have next Tangyu Huang from Chalmers University, and he will talk about quantum process tomography with digital twins of error matrices.
Thank you for the introduction, and thank you for all still being here. At this moment, I will try to finish my last talk as soon as possible. So hello everyone, my name is Tangyu Huang, and I'm a researcher working at Chalmers. In our lab, we are aiming at building a larger scale quantum computer with superconducting circuits. So today I'm going to share with you our recent progress on this quantum process tomography. So here's the outline. So I will first explain the problems in the quantum process tomography, and then we come to the method we proposed to solve this kind of a problem. And I will also present some numeric and experimental demonstration on our method. And finally, we come to a short summary. So firstly, I believe most of you are familiar with this quantum process tomography. So in the lab, if one wants to perform the quantum process tomography, so firstly we need to prepare the initial set of initial states, and then measure the final states after applying an unknown gate, which is we want to reconstruct it. And after collecting all those experimental results, then we do the tomography analysis, which is to estimate the process metrics, for example, chi metrics, and by fitting the experimental data. But the point is, in the lab, we cannot prepare perfect initial states, and we also cannot measure the states perfectly. So then it causes the noise in measurement. So that's the reason why this spam error appears in the quantum process tomography. But how does spam error degrades the performance of the quantum process tomography? So first of all, in a standard quantum process tomography, we presume that state preparation and measurement are perfect. But the reality is it's not. So that's why the standard quantum process tomography is safe inconsistent. But however, if one knows the exact noise properties, and then we can do the safe consistent quantum process tomography. But the point is the exact noise property is really hard to reconstruct in the lab. So then it comes to our method. So we are trying to approximate this noise in probes. So since it's approximation, so we call it error mitigated quantum process tomography, and it's nearly safely consistent. And how to formulate these methods? So first of all, we did the same as the standard quantum process tomography. We want to estimate this unknown gate, for example. Then we collect over all those experimental data, since because it's noisy, it's because the spam error. Then we do an extra experiments, the identity quantum process tomography. Since the identity here means the idling, so just doing nothing. And because of doing nothing, so we assume and we believe that spam error are all included in this quantum identity process. So then we utilize this identity kinematrix to reconstruct, to revise the ideal probes. With this revised probes, then we can do the quantum process tomography like more reliable. So to demonstrate, to validate our method, we design some numerics. For example, we introduce two kinds of errors. The coherent errors means like because when you prepare the states, you have to apply a lot of a sequence of the single qubit gate. So the coherent error here is introduced by like this unitary mismatch, and also we define this incoherent error. We take it as a depolarization error channel. So then we can quantify the total spam error with a lambda total. So this is a numerics. We also have the experiments accordingly. So we perform the experiments on two different devices, device A for the 1 qubit gate and device B for the 2 qubit gate. And here we take the randomized benchmarking fidelity as our reference to make sure that the gate we performed is actually the exact, at least close to the ideal gate. And then in experiment, how to introduce this spam error, of course, introduce more error is more easier. So for example, for incoherent error, we simply revise the well-calibrated reset pulse, readout pulse. And also for the coherent error, we simply revise the pulse for the single qubit gate to introduce extra spam error deliberately. So here's the result. Numerics and experiments. Experimental results are also like our EMQPT. It has better performance than standard quantum process tomography. Okay, so now we've already realized high accuracy quantum process tomography by integrating this identity extra experiments. But we still want more. For example, we want to pursue the high precision. So to do this high precision fidelity estimation, one needs repeat 1 and 2 steps for many times, which means we need to repeatedly measure the identity quantum process tomography. And then to take the average number of those measurements, then we can get this high precision result. But the thing is this is quite expensive because you need to keep running the identity process tomography. So since the spam error is actually independent of the gate operation, so it's natural to think about how about using some machine learning model to learn this statistical behavior of this spam error. Yeah, the answer is yes. So we want to learn this error behavior by a generative machine learning model. For example, here, the training data is error matrix, the kinematrix of this identity process. So we transfer to a 16 times 16 piecewise image. Then we put all those experimental measurements to a generative machine learning model, which is a variational autoencoder. It's a really not complicated machine learning model. So Then after training this machine learning model, so ideally we have this well-trained machine learning model that can produce the similar statistical behavior of this spam error. So then we can generate arbitrary number of these error metrics instead of doing real experiments. So combine this well-trained machine learning model and the standard quantum process tomography, one can get actually high precision fidelity estimation. Then we here I want to emphasize why we need this machine learning to learn this spam error. For example, if we collect a lot of error metrics by doing realistic experiments, then we do the gate quantum process tomography, one can get this fidelity distribution of this EM2BT. So you can see if you do not do some data processing, you will always find some anomalous appears among those experimental measurements. But instead, we put this experimental data into a machine learning model to create a digital twin of this spam error. So the digital twin captured actually the major error pattern of this spam error. So the one can get this less deviation fidelity distribution from this digital twin. So which means that our machine learning model actually learns the major error pattern from the training data to find those anomalies from the experiment environment. Okay, we also did some 2-qubit gates, and our master EM QBT and the machine learning QBT has better performance than the standard QBT. And also here's the summary. So first of all, our master achieved at least an order of the magnitude improvement in accuracy first over the standard QBT. And also our master has been verified for 5 different superconducting quantum chips. And also in addition, our generative machine learning model improved the precision up to the second momentum. And yes, because our method extends the usage boundary of the QBT in presence of the spam error. So our code is available online, so just play with our method in your lab. And I want to thank to the collaborators, team from Chalmers and Aalto University. And thank you for your attention.
We have time for one question. Then I'll ask one. For me, these techniques, I was wondering, how do we actually then loop back to the experiment, right? Is there something we can infer from the results that we can directly then implement in our experiments to improve the fidelities?
Yes. Yeah. So that's why I keep saying the machine learning model or the master EM QPT is still really, you can see it's really straightforward. You just, instead of just doing one quantum process tomography, you do an extra identity process tomography. Identity means doing nothing. Nothing is really easy to implement. So it's really ready to go for the experiment to provide more accurate result from the quantum process tomography.
And how long does the machine learning loop actually take? It's this.
Yes, that's why I mentioned here is a variational autoencoder is really a model for example, 10 years ago has been proposed. It's a really simple one because you can see because here the data complexity is for example 16 times 16 is really small. It doesn't take a long time. For example, for 2-qubit gate constrained the digital twin is just 1 minute. 1 minute, yeah.
Excellent. All right, before you all go out to lunch, we have Stefan again who has a few questions. And let's thank all of the speakers of this session.
Just formalities from my side. So if you have a poster today, poster session today starts again at 2 p.m. downstairs. Please bring your poster downstairs, put it somewhere, and attend it from 2 p.m. to 3:30. Then we have lunch outside, same stations as yesterday, upstairs and in that room over there. Then, reminder, there are workshops today. It's scaling, it's Orange QS, and it's quantum machines. In the first session, scaling and quantum machines. Scaling and Orange QS. Scaling is on this level in Scania Holland. Orange QS is, I need to check which room, but we'll guide you, have people guide you. The quantum machines workshop will also be in Scania Holland over there. So the same room, in case you are both, you can just stay. And then we continue in this room at 4 p.m. with the next session and the last session for today. And just in case you plan to go to the hotel or something earlier, for the conference dinner, we gather here and go there together. You don't need to organize your own way of getting there. Awesome. Enjoy lunch.
Okay, there we go. All right, welcome to the last session of the day. Just so you know, you will receive information about the conference dinner at the end of the session, so don't worry about it. But it does mean that we need to be on time today. So yeah, I'm Joonas Govenius. Most recently worked at VTT, but nowadays I'm the CEO at Arctic Instruments, working on TUPAs these days. So great to see all these interesting talks on the topic. The first talk is by Sanbo Chang, and he will tell us about waveguide, parametric amplification, and tunable frequency conversion. So please.
You hear me? Thanks, Jonas, for the introduction. I'm Sanbo, research scientist working at Professor Nakamura in Riken, Japan. Today, I'm happy to share with you our progress on making JTuber, and I would also like to take this chance to thank the organizer for SQE for this wonderful conference, so we have this opportunity to share with you. So to begin with, I would like to talk about some background information about parametric process in nonlinear waveguides. Basically, using Fourier mixing gain as an example, energy conservation tells us how we should be pumping our device. For example, we have to pump at the half frequency of the sum of the signal and idler. So that's why when we drive a tuber in Fourier mixing gain at 8 GHz, we can see gain at 7 GHz and 9 GHz, for example. But this is not sufficient, as you may already know. We also have to fulfill phase matching in this case. And for Fourier mixing gain, the phase matching is given by the delta K term here. We have the linear term in bool. So basically, they are slightly negative. They could be due to the CJ. They could be due to the discreteness of the unit cell. However, the red terms corresponding to nonlinear phase mismatch can be quite large because they correspond to the gain process that we drive really hard to get gain, but then we also would drive the cell phase and cause phase modulation. So naturally, if we don't do anything, the delta K is going to be negative. So there are now actually multiple ways to solve this problem. And out of those ways, we are particularly interested in dispersion engineering. The reason is we can now use some passive structure that allow us to use a linear mismatch to put some terms into the linear mismatch. So sorry. To put some terms into linear mismatch to make it more positive to compensate for compensate the negative terms in the nonlinear phase mismatch terms. The great thing about that is we don't have to supply a DC current or DC flux to operate the tuber in that case. And one example in implementing that is so-called resonant phase matching. And the way it works is to insert a band-stop filter, basically a lump element LC filter, FE4 unit cell, for example, along the J-tuber line. And by doing that, we basically create a stop band at some frequency, which is very sharp. But the stop band is not what we are looking for. What we're looking for is actually the dispersion relation where we plot the wave vector versus a frequency. In this plot, we can see that comparing to the dashed line, which is with no resonator, now with the solid line with the resonator, we actually can see that if we put our pump frequency at this different red, yellow, and purple point, we can achieve different amount of positive KP. And if we put some positive number into KP and put it back into this equation, we can see that we can cancel out the negative term in the nonlinear phase mismatch and hopefully bring delta K back to 0. And this is basically the way we can achieve phase matching and then high gain in this Fourier mixing gain configuration. So now let's say RPM J-tubers or RPM itself is pretty useful. How do we achieve that? As it turns out, its implementation can be quite challenging. The reason being, one way is to use lump element resonator. They are very compact in size, so we can put them in a very dense manner. For example, FE4 cell, we have one resonator. However, to make them very small simultaneously with very high accuracy in frequency, this is quite difficult in terms of fabrication. So this makes fabricating them quite challenging. An alternative way is actually to use waveguide resonator. I think as we can tell, waveguide resonator, they're relatively big, and usually we can achieve a pretty good frequency accuracy out of this geometry. However, due to the big footprint, we cannot really put them in a very dense manner. We can maybe put it every 10 cell or even more. And as a result, we don't really have a very dense phase correction that we can achieve using small lump element resonator. So our question here to ask is, can we have a design that can achieve simultaneously a high phase correction density while making it easy to fabricate like a waveguide resonator, RPM screen? The answer is actually yes. But to understand how we can do that, let's see what the existing schemes in RPM are doing the correction. So we basically try to couple one resonator capacity to FE4 cell at one cell only, and also in a waveguide case, maybe 10 cell or more to one cell only. As it turns out, there's no reason that we can't do this. We can try to actually couple one waveguide resonator to multiple cell, for example, 10 cell, and we can do this in a continuous manner. So we have resonator 1 talking to the first 10 cell, the second 10 cell talked to a second resonator like that. And as a result, we do not miss out any single unit cell in this J2 line. And as a result, we hopefully can actually correct for the phase mismatch in a very continuous manner. So the implementation is actually very simple. We can actually consider the same kinds of waveguide that allow a couple groups are already using. This is so-called a fishbone waveguide. We obtain the shunt capacitance by having interdigitated capacitor-like structure. And then along the center line, we have the series junction. So we form this LJ and CG unit cell. We just have to open up one side of the open stub, the tip, and then we allow a gap capacitor to basically talk between the tuber line and then the waveguide resonator. And hopefully then we can couple this 10 cell or 13 cell to this waveguide resonator. And the advantage is what I mentioned earlier, so the then phase correction with even fewer resonators than the lump element case. And also because of the large footprint was a problem, but now we can actually couple a bunch of cells to the same resonator. It is no longer a limitation in terms of getting dense phase correction. But before I can use waveguide resonator to do resonant phase matching, there's one more point I would like to bring about. So as people have tried, for example, from IBM, also from MIT, they have seen that if they try to use transmission line or waveguide resonator, because of the existence of the higher frequency mode, this actually would talk to your gain spectrum and create some distortion in your gain spectrum, like dips around the gap. So this is something that you don't want when you want to make a J-tuber. If you think about our device, it would be something like 10 cell coupled to one resonator pad, which extend to a number 4 resonator on top. In a pawn-like coupling structure, which is typically found in the RPM implementation, the coupling string would actually just go up in frequency to almost infinity here. If you think about the fundamental mode is coupling to the resonator pad in this manner, we basically have a very long wavelength and only a portion of the wavelength is exposed to the resonator at a time. But as we consider the high harmonic, for example, the third harmonic of this resonator frequency, we can see that as the wavelength is, as the frequency is going higher, we have a higher phase change per unit length along the tuber line. We actually start to see we have positive term and also negative term in terms of a waveform, voltage phase, coupled to the resonator. And you can see that part of this induced charge onto the resonator open circuit end will actually cancel. So we actually obtain some cancellation comparing to a pawn-like coupling. So at some frequency where you can fit a complete waveform into the resonator, in the resonator, the length of the coupled section of the tuber line, you can actually see that the positive term and negative term would be fully canceling each other. And as a result, you actually would decouple that frequency from between your tuber line and then your resonator for the phase matching. And going up back to fifth harmonic, you would actually gain back some coupling. But again, because of this effect of cancellation, you can actually suppress some of the coupling. As it turns out, this kind of suppression can follow a sinc-like function pretty well. And by designing the number of M, the number of cells that you couple to one resonator, you can basically put the blue dot and the red dot into the notch and essentially decouple the high frequency mode from your resonator. So hopefully then you can gain back the red gain curve on the left-hand side by using a waveguide resonator. So to check if this device or this idea works, we fabricated a device with 1,800 cells roughly in a 5 by 50 millimeter chip configuration. And then by looking its transmission through a fridge, we can actually see that it delivers a 40 megahertz of gap. So this corresponds to around 0.5% of frequency spread. And then by driving the device a little bit below the gap frequency, maybe around 7.95 gigahertz, we can see we obtain 20 to 29 dB of gain for the frequency below the band gap. So a moment ago, I was showing the gain curve that was actually obtained by sandwiching the device using attenuator. So this gives us an intrinsic gain performance of the tuber, but we cannot use a tuber with attenuators attached to it. So we now try to connect the device to a qubit readout circuit where we don't have attenuations, and this is the gain curve that we get, we still get over 20 dB of gain over 4.2 gigahertz. So I would say that this tuber is still performing quite well. And then we also attached across the tuber waveguide QED calibrator device as a qubit coupled to the line. So we are seeing that our tuber only adds 0.72 quanta of noise at 20 dB gain at the qubit frequency. And the saturation power is around minus 102 dBm. So that wraps up the work on tuber. So we have demonstrated DC RPM allows to make a J-tuber relatively easily with resonant phase matching mechanism. So now we turn our head to looking at another device. So before we start, we have to look at the concept again. So a moment ago, we were looking at Fourier mixing gain. Essentially, we are trying to convert the pump photon into a signal photon and idler photon. But here, this equation is going to be a little bit different. Instead of splitting the pump photon, now the pump photon will actually supply the energy to fill the gap between the signal and idler. So we can actually swap between the signal and idler photon like that. To put things into numbers, we can be pumping at 2.5 gigahertz, and we hope to see if we can couple between 6 and 11 gigahertz in this case. As you would expect, for this process, we still have to fulfill the phase matching condition. So here is a case with no phase matching. So we can see that this purple curve corresponded to the total phase mismatch. And we can see that this curve is always below 0. No frequency in the 0 to 12 gigahertz range is actually having a delta K equal to 0. And as a result, when we look at the transmission at the same frequency, not much is really happening. But if we can achieve phase matching, for example, by using RPM method, so we can actually bring this curve up in vertical direction, for example. And by bringing this up, at some point, you will see that you now actually have X causing. For example, around, this is 6 gigahertz roughly. And at this frequency, if you look at the transmission, now you can actually see that there's a big notch. So what happens is that you send a frequency at 6 gigahertz, but then because your frequency is actually being converted to 11 gigahertz, they're not coming back to your VNA. So the VNA thinks that it's actually a loss, like a notch as a result. So what is really interesting about this method is now, because of the RPM structure, is kind of tunable in terms of how much phase correction you can get. So by pushing the pump frequency a little bit closer or a little bit further from the band gap that you create using the resonator, the bandstop filter, you can actually select how much phase matching you put into the KP term, and you can shift this curve up. Effectively, you shift the X causing laterally. And as a result, you can actually tune your pump, your conversion frequency, the target frequency, in situ without any DC flux bias. And one more very encouraging situation is the conversion efficiency can be simulated using harmonic balance. And in this case, we can see we may be able to achieve a conversion with a bandwidth with a conversion over 85%, reaching 500 megahertz. So to see if this idea really works, we fabricated a relatively short device. And this device is short because we don't really need to push a gain. We just need the conversion to happen completely from one frequency to the other. And then we try to first cool down this device across a 50 ohm transmission line to see the loss in this device. And we are measuring basically less than 0.5 dB of loss in most of the frequency range. And then with 12 gigahertz reaching maybe 0.6 dB of loss. So if you look at the PMR line width, so phase matching resonator, we are basically getting 6.4 megahertz, which is very close to the parameters that can be fitted to this device from our design. So now we try to drive our sample at a frequency slightly below the 2.69 gigahertz gap that we were showing a moment ago, and we obtained this transmission. So this is, as I explained earlier, because we are sending and receiving at the same frequency, and as a result, we will be seeing a dip, we are losing photon because they are converted to the other side, and the same thing happens on the high side. So the gap can be as large as almost 1 gigahertz if you consider the width that is more than 10 dB of loss. If you want to use this as an isolator, this is already a relatively useful device. So next here, I'm trying to see how much I can tune the frequency. As it turns out, we can actually move the target frequency from 4.8 gigahertz all the way to 6.6 gigahertz. And this is all done by changing the pump frequency and pump power alone without any DC flux, DC current or flux bias change. We can also feed using harmonic balance to the data, and we can see that we have this kind of power chain. The power required to achieve good conversion going up the target frequency is actually dropping, and this can be explained by the situation that we want to keep the sine square term constant. We want the full transmission. And then if you look at the L is fixed, the G is actually depending on the Ks and Ki. As frequency goes up in this curve, Ks, Ki increase, so we have to drop the IP to compensate for, to make G constant, basically. So this is why the power is dropping. So next, we want to see if our device can actually provide good conversion. At the moment, we don't really have a full system or wideband frequency calibration, so we don't really know how good the conversion is in the individual direction. But it turns out that we can actually still look at the conversion by sending a low frequency, and then we look at the high frequency. That is a red curve that we get. The blue curve corresponds to when we look at the low frequency and send at a low frequency and look at low frequency. The same thing happens on the high side. But as it turns out, there is a small trick we can apply, which is a self-calibration. So if you think about a device as a through line, when the device is off, when we send something at a low frequency, it receives the loss at the low frequency. It also receives the gain at the low frequency. And then the same happens on the high frequency. So we basically get a room temperature measurement for the low and high frequency transmission through the cryostat. As we turn on the converter, if we send something at low frequency, the converter would bring it up to a high frequency, and then we can now look at the high frequency. We actually obtain a transmission from low to high. This is a typo. And we can do the same thing by sending at high and listen at low. And if you look at these four terms, we can actually see that if we take the product of the bottom two divided by the top two, we can isolate out the product of the conversion factor of the converter alone. So now we can at least look at how much total conversion loss if we lump them together. As it turns out, this number is as small as less than minus 1 dB over a range of 450 megahertz. And if you believe that these two numbers are almost the same, so we can say that individually, maybe we can reach over 89% of conversion over 450 megahertz for this device. So one question to ask is, if we have noise coming back through this converter, what really happens? We can see that in the forward case, we have this dip, and then we have this conversion amplitude, and we try to reverse the direction of the probe. We actually can still see some of the signal coming back, but this level is around 18 dB lower. So we essentially has an isolator that prevents signal from going back to the frequency that we convert from with 18 dB of isolation. To sum it up, I hope I have convinced you that DC RPM is a relatively simple structure and it works quite well. And we have demonstrated this with a J-tuber having 20 dB of gain over 4.2 gigahertz, adding a noise of 0.72 quanta. And in the meantime, we also try to demonstrate a converter based on the same mechanism with efficiency reaching 90% over 500 megahertz. So the next thing that we want to try is actually to see if we can combine the two together. For example, if we have a frequency for the readout at around 11 gigahertz, which is a high frequency readout that people are up to these days, we can actually use an edge drop filter to combine that with a converter pump at 2.5 gigahertz. And they can go together to the converter. We can now convert the 11 to the 6 gigahertz, and then they can now pass through a low pass filter at 10 gigahertz, which was otherwise too low for the original frequency for the readout, to prevent any noise from the backside to go back to the readout cavity at this point. And then we can put them together into a second edge drop filter. We would drop the 2.5 gigahertz. We can now add a 7 gigahertz, and we can put them back to the tuber with a gain of 5 to 9 gigahertz. And together, we can now amplify the qubit information signal at 6 gigahertz without affecting the readout cavity, while everything is on continuously, hopefully. So if you're interested in the structure of this edge drop filter, you can take a look at this reference. So hopefully, at one point, we can put everything together in a single package, and we can basically make a readout train without circulator. This is one thing that we may be trying soon. Thank you.
All right, thanks so much. Questions? There are some. You'll get a microphone.
Thank you for the very nice talk. I was wondering, since you want to integrate everything on the same chip, how much conversion efficiency do you think you need to have to integrate this with qubits? Thank you.
I haven't really considered that, but one thing I would like to point out is with a tuber with high gain, we are already stuck at 0.5 in terms of efficiency of the readout. So if we have a converter at 0.9, I'm guessing the hit is not so bad. But then I also want to point out, like we have the conversion as a dome shape in a sense. So the 0.9 or basically 89% is talking about the edge. So at the center of this dome shape, if you put your qubit width over there, you can get already like a 90% or maybe 95%. So I don't have a number, but I think the impact is small.
All right. One more quick question. There's Hampus.
Thanks for a nice talk. My question is regarding these resonators that you couple to several unit cells. Isn't there a risk that the signal essentially leaks via the capacitor to the resonator and then passes by essentially all the unit cells of the tupa and then goes back into the line? Do you have anything to say about that?
Yeah, I get your point. So this is a very good question. In this case, we can consider how much coupling cap we really have. So for example, this one is a little bit higher, to be honest. But for the previous J-tupa, we're talking about 1.5 femtofarad. So if we consider the junction has a series parallel capacitance of, let's say, 50 femtofarad, for 10 cell, we have still maybe like 5 femtofarad. So this bypass is actually quite small comparing to the junction capacitance alone, I would say. So this is a valid worry. So we cannot have this number being too high. But then in this parameter regime, we don't really see problem.
Thanks.
All right, great. Let's thank Sanbo again. And next we have Holly. Yes, talking about low loss resonant phase matched JPA.
Hello. Hello everyone, I'm Hao from the EPFL. Today I'm going to present our recent work on the low-loss resonant phase matched Josephson traveling wave permanent amplifier. So J-tupa is very promising for scalable frequency multiplex qubit readout due to its large gain bandwidth, nearly quantum limited noise, and also the large dynamic range. There has already been many implementations since the first one in 2015 by the MIT Lincoln Lab. For example, the curve reversal tupa and also the 3-remixing tupa based on the Snell or the RF squid. However, most of the implementations requires using the dielectric materials. This will introduce 0 dB insertion loss, which will degrade your effective signal-to-noise ratio improvement. And also, when you want to use your tupa as a squeezing source, this kind of loss will also degrade the squeezing performance. So in general, a low-loss fabrication process is preferred. And it was until recently people have demonstrated the low-loss tupa. For example, the work from Nakamura's group, and also in the talk you just heard about, which is also from Nakamura's group, and also the low-loss Floquet tupa from the MIT. And we prefer the resonant phase matching schemes due to its narrow and power-independent stop band, so this will simplify the tupa operation and the design. However, the implementation of the resonant phase matching schemes on a planar structure is really challenging because this will really requires a large footprint. And this will reduce the number of chips per wafer and also complex your packaging design. And our method to break this footprint and the performance trade-off is using the DUV lithography to define the waveguide capacitors and the phase matching resonators. As you can see, we have in total around 140 chips on a single 4-inch wafer due to our compact chip size. And for now, we are still using the hybrid fabrication method, which means we are using the E-beam lithography to define the junctions and the patches to connect the junction to the signal line. And we are sweeping the junction size on the wafer just to tune the critical current so we can have the device reaching our target impedance. And recently, we have updated our archive preprint. If you are interested in our fabrication process, please have a look. So here is how our device exactly looks like. Basically, it's a uniform J-tupa. So in total, we have around 2,000 junctions, and we loaded the phase matching resonator every 8 unit cells. And you can see the phase matching resonator on the right part of the image, which are colored in the green part. And in the bottom zoom-in image, you can see the interdigital capacitor and the meander inductors, where they both have the critical dimension of only 400 nanometers. And in the middle of the image, you can see the coupling capacitor and the capacitor to the ground. On the bottom right, you can see our Josephson junction, which are fabricating a method similar to the Manhattan-style junctions. To measure the performance of our device, we put our tupa and the through line and also a waveguide QD device between the cryogenic RF switch. So we measure the insertion loss of our device. As you can see, it's pretty low. It's below 1 dB until 8 gigahertz, and at a higher frequency range, the loss increases a bit. It's actually not from our device, but actually because of the higher reflection from the packaging. And if you take a zoom in around our stop band, you can see that the stop band is pretty narrow. It's only 43 megahertz. even if with a critical dimension of only 400 nanometer from phase matching resonator. And this narrow stopband actually indicates that the frequency scattering is less than 1%. And with a pump, we can measure the gain profile of our tuba. It shows a broadband gain and with a maximum gain above the 20 dB. And it's worth to mention that this measurement is done without attenuator before or after the tuba. And we also characterize the added noise and the power handling ability of the tuba. To do this, we need to know the absolute input power at the tuba input plane. And the method we are using is using a waveguide QED device. Basically, it's a frequency tunable qubit strongly coupled to the waveguide. By tuning the external flux, we can change the qubit frequency from the sweet spots around the 8 gigahertz all the way below 4 gigahertz. So at each qubit frequency, we do a power sweep. So at the high power, the qubits are saturated, so you got a perfect transmission. At the low power, the qubit behave as almost effectively perfect mirror, so you can see a dip in the transmission. And if you check the transmission at the qubit resonance frequency, you can get a shape like showing on the right. So the data are color-coded in the probe power. So we do a 2D fitting of this transmission data versus the probe frequency and the probe power. Then we can get the total attenuation from the room temperature to the tuba input plane. So what we are showing here, actually including additional 40 dB attenuation we put at the room temperature for this calibration. And you can see a linear dependence of the attenuation versus the frequency. So we fit it to this blue line. And the shaded region corresponds to plus minus 1 dB reference to this blue line. Since we have the calibrated input power together with the noise floor measurement with the pump on and pump off, we can get the added noise of our device. So on average, we achieve 0.4 photons per second per hertz above the standard quantum limited in the calibrated frequency range. With this pretty small added noise, we can achieve a pretty good signal-to-noise ratio improvement. In general, it's around 10 dB. And we also carefully measure the power handling ability of our tuba. So we measure the 1 dB compression point is around minus 102 dBm in the calibrated frequency range. And we want to point out that it's not enough to just measure the 1 dB compression point. It's also important to check your phase response. So especially near saturation, that's why we're reporting this something we call the 5-degree phase distortion point, which we define as at which input signal power the phase response is actually a 5-degree difference compared to the small signal regime. And we actually noticed that for certain frequencies, this phase distortion can happen earlier than the 1 dB compression point. And just to visualize this effect more effectively, we do this kind of constellation diagram measurement. So basically, we send a signal pulse of 2 microseconds, and we're doing the integration only 300 nanoseconds after the pulse started, just to avoid the delay from the line, and also the transient dynamics of the tuba. And before the saturation happens, you can see the central spacing scales linearly versus the signal input power. And also they are remaining the circular shape. However, if you are near the saturation, the nonlinear phase response will start to rotate your IQ blobs, and also they will deform. They are no longer remaining a circular shape. So this tells you that you need to be more careful for the qubit readout calibration, especially when you're operating near the saturation point. Since tuba is usually motivated for using for the frequency multiplexed readout, you should also check the intermodulation distortion. So that's why we send 2 tone with equal power centered at 5 gigahertz and with 5 megahertz detuning between each other. So we sweep the input signal power and check how the 3rd order or the 5th order products change versus the input signal power. And by extrapolating the trend at the low signal regime, we can get a 3rd order intersection point, which is around minus 91 dBm, and is actually 10 dB higher than the 1 dB compression point for this signal frequency. And this 10 dB difference is actually consistent with the prediction based on simple qubit transfer function model, which are also used in this intermodulation distortion quantization paper from the Andreas Worrell's group. And we also want to understand what limits the maximum gain inside our tuba. So we sweep the pump power and see how the gain and the signal-to-noise ratio improvement change versus the pump power. So this black dashed line is the operation point that we optimize for the broader and fatter gain profile. And when the pump power is actually above this point, we see the gain continue to increase. However, the signal-to-noise ratio start to drop very fast. And we believe this is the indication that the onset of the parametric oscillation, which might due to the non-uniformity of the Trussman junctions, which cause the internal reflection. So to conclude, we have demonstrated a resonant phase match J2PA. So the main advance of our work is not just a single record performance metric, but rather the combination of the low insertion loss, broadband gain, a useful dynamic range, and also near quantum limited adenoise, but together with a compact footprint in a planar architecture. And we believe this could be a critical route towards a scalable cryogenic microwave hardware for larger quantum processors. And we are currently developing a fully DUV-based low-loss fabrication process. And I would like to thank all the LPQM circuit team members. And we are also hiring the postdoc.
All right, thank you. Questions? There's one from Simone.
Maybe you mentioned it already. The gain, is it an on-off gain or a true gain?
It's a true gain compared to the through line.
Okay, thank you. And what is the additional loss in the device when the device is off? How much loss do you have essentially?
It's showing the top panel, so it's pretty low, below 1 dB, I would say, safely.
All right, thank you so much.
One more quick question. Okay, maybe in the interest of time, we move on. And then we see it there now. Yes, okay, great. So Markus Griedel will give the next talk.
On? Okay, yes, thank you, and also welcome from my side, and welcome to this talk. I will explain in the next couple of minutes, introduce a low-loss material that can be used to protect cryogenic quantum applications against infrared photons. Okay, we have to do it like this. Yes, as you all know, infrared photons influence superconducting devices by breaking Cooper pairs and therefore introducing quasi-particle excitations that then influence our devices. For example, superconducting resonators, quality factors changes due to infrared impact, which can be a feature as, for example, in microwave kinetic inductance detectors, or it is a problem as in our superconducting qubit community, and therefore of research interest over the last decades. To understand where these photons come from, I want to point out the frequency spectrum. So our superconducting qubits live in the gigahertz frequency regime, so corresponding to centimeter wavelengths, and the superconducting gap, for example, aluminum, which is typically used, is in the millimeter regime. And so every photon carrying more energy, so from the superconducting gap all the way to the visible light, can in principle introduce quasi-particle excitations and therefore losses in our qubits. To limit thermal quasi-particle excitations, we cool our qubits usually down in such dilution refrigerators to millikelvin temperatures, but infrared radiation from room temperature and elevated temperature stages can still leak through, and for example, even infrared radiation from a few Kelvin is beneficial to break Cooper pairs and therefore harm our systems. So typically what we do, we put our samples in closed shielded box in the bottom, in the cold stage of our cryostat, but we have to read them out somehow, which we do with microwave cables, which has a dielectric, which is typically Teflon, which is transparent to most of the infrared spectrum. What you can see here in this measurement, where we again have this wavelength range from nearly optical to where our superconducting qubit frequency lives. And what you see here is the absorption spectrum of Teflon. And as you see, it's transparent over large ranges. And the Beer-Lambert law tells us for an absorbive material that the transmission is decays exponentially with the length and an extinction coefficient mu. And what we find in our qubits is that the length of the Teflon is not sufficient. So we have to replace the Teflon by a material with a higher extinction, or in other words, put in an infrared filter that has a sharp cutoff between the superconducting gap and where our qubit frequency lives. Yeah. Okay, so we want for this not only a material that has a large infrared blockage, but also a good microwave performance. So we decided to look into sapphire, which is known for its very low microwave loss. And so what we do in the first point, we look at spherical sapphire spheres in a medium where me theory tells us that there is some resonant extinction at a certain wavelength, when the wavelength and the size of the sphere roughly falls into the same order of magnitude. And that's actually what we then also calculate here for a sphere of 170 micrometer diameter. We see exactly this resonant extinction with a sharp cutoff above and a constant tail towards lower wavelengths. So this is what we want to use now, since this resonant is dependent on the size of the spheres. So if we put in multiple spheres, we can think of making a broadband filter with a sharp cutoff given by the largest sphere in this mixture. And if we calculate, if we do this, we can come up with a filter design sketched here with multiple spheres, which then scatters different wavelengths. And if we calculate now the extinction of such a mixture now on this right axis on a logarithmic scale, we can see that the extinction of this mixture should be quite broadband and has a sharp cutoff that is tunable by the size of the particles inside. And we fabricate now exactly this mixture out of these sizes we modeled here on the left side and measured this in an infrared spectrometer. And what we see over the infrared range, that we have a large absorption close to unity with a sharp cutoff in the far infrared range. And in principle, this cutoff is tunable by the particle sizes we put into this mixture. But as I said, that's only one side of the story. The second part is in this gray area in the microwave frequency regime where we want to have very high transmission. So to measure that, we built a prototype filter where we replaced in a coaxial architecture over a length of 8 millimeters the dielectric by the sapphire compound and measured it in a dilution cryostat at millikelvin temperature. And what we found is, what we can tune them is we get a transmission of better than 0.4 dB for frequencies below 10 gigahertz and a reflection of roughly minus 30 dB over the full microwave frequency range. In the last minute of the talk, I want to put these two sides together and compare it to another material we typically use for infrared filters, EchoSorb CR124. And if we look now in this far infrared regime, we can see that the sapphire compound material is a factor 2 to 3 smaller in extinction than EchoSorb. But to give you a number, for example, for the prototype I showed in the previous slide, this would result still in a attenuation of better than 180 dB in the full infrared regime. And if we now look into the other side, into the microwave regime, we have now shown this on a logarithmic exact extinction coefficient, and here we achieve extinction of a factor 10 to 100 lower than typical EcoSorb materials, which put us exactly at this minus 0.4 dB transmission in the microwave regime. To conclude, we all know that Teflon does not shield against pair breaking radiation, and we have to use some infrared filters in our applications. And I hope I've shown you that sapphire spheres are a promising candidate for that. And with this, I come to the end, and I want to thank my colleagues at KIT in Karlsruhe, especially Biba and Yves Laurent, who helped perform the spectrometer measurements. And I also want to thank you for your attention, and I'm happy to answer one or two questions now.
Thank you. Perfect timing. So we have time for questions. Andreas.
Can you explain a bit more how your infrared spectrometer works and how it was calibrated?
Yes. So this is a commercial Bruker spectrometer and using a thermal radiation source, the Globa. And the detector are different detectors depending on the wavelength regime. So for the most challenging part, so the wavelengths in the far infrared regime, it was an 1.6 Kelvin silicon detector. Yeah.
So did you measure the quasi-particle density like after you use this material? Like did you compare the with and without this material?
Yes, that's a part that's maybe still a bit under investigation. I probably don't have time to go into all of it. But we built up a small setup where we have a cold infrared source in a cryostat and a qubit, and can measure then the impact of the infrared light onto the qubit and put in different materials to measure their infrared absorption probabilities at millikelvin temperatures. Here, for example, we measured the decay rate of a qubit depending on different blockage material put in. But we can talk about details maybe afterwards.
All right, thank you. Okay, this one, right? Okay, so next we have, yeah, that should work, I think. So next we have Kian Jansevar talking about voltage tunable resonator using quantum phase slip nanowires towards a parametric quantum amplifier.
Thank you very much. Thank you very much for the introduction. And it's a pleasure to be here and present our group's research on parametric amplification. So today I'll talk you through our progress towards voltage tunable quantum amplifiers using quantum phase slip nanowires. We'll start off with an introduction to the device design and geometry that we've chosen. And then we're going to move on to seeing that this device can be operated in two distinct modes. The first of which is a voltage tunable resonator, in which we can electrostatically tune the resonance frequency of our resonator. And then we'll move on to seeing that the same device can actually be operated as a parametric amplifier, in which the amplification can also be electrostatically tuned with an applied gate voltage. So in order to understand this duality, we're going to revisit a picture that we're all very familiar with. And we've borrowed these diagrams from de Graaf's charged quantum interference device paper. So we have two junctions in parallel, and the Cooper pair tunneling events are happening across both of these junctions. An applied flux between them is leading to the interference between these weak links. Now, in order to look at the dual of this image, we're going to flip the insulating and superconducting regions together. And we're going to see that we'll end up with two very narrow conscriptions which we'll call our nanowires. The quantum object that's now tunneling is no longer the Cooper pair. Instead, it is a flux quanta or a fluxon. The interference between these two nanowires, it's set by the charge on that superconducting island. All this goes to show is basically that we have a dual between the squid and this new quantum facelip dual equivalent of it. And this means we can revisit a lot of devices that are using squids and Josephson junctions and now embed these nanowires instead. But this has already been done. This is not necessarily new. And most notably in 2018, de Graaf and authors demonstrated a dual to the squid, which was the charge quantum interference device. In their device, they had two superconducting nanowires with a superconducting island between them. The charge on that superconducting island was being modulated by an applied gate voltage that we see to the right. More recent results demonstrated that you can use the same duality and nonlinearity, in fact, to realize qubits as well. So here we're seeing a demonstration of a facelip qubit, which is embedding one of these quantum facelip nanowires within a highly inductive environment, similar to what we'd see with the transmon dual as well. Now, in our research group, we're also looking at different Josephson junction-based devices and trying to come up with the dual versions. And we've primarily focused on the Josephson parametric amplifier. So in this case, we've taken a look and we've come up with the dual version of it without the Josephson junctions and instead embedding the quantum facelip nanowires. And what this is essentially allowing us to do is to go from a control with current and magnetic fields towards voltage and electric fields. In order to design such a device, there are several considerations that must be taken into account. To see the quantum facelips in the first place, we need the cross-section of the nanowires to be on the order of magnitude as the coherence length of the material that we're using. Now, in the case of niobium nitride, being at around 8 nanometer thick niobium nitride puts us well in the regime to see quantum facelips. So we'll start taking a look at the device in more detail. Here we have an optical micrograph of the device. The darker regions is our substrate sapphire. The rest of that is niobium nitride. So we have a feed line. Capacitively coupled to that feed line is a quarter wavelength resonator. And if we zoom into that resonator, we'll notice that there are two superconducting nanowires embedded within it. Now, these nanowires have a superconducting island between them, and that charge on the island is exactly what we're setting with the gate electrode shown top right over there. So essentially, from here on forward, any reference to a gate voltage that's being applied to our device is being directly applied to that gate electrode. The first test that we did to see if this device is truly nonlinear or not is to have a very simple measurement scheme shown over here. We have a carrier frequency being sent down the feed line, and we have a modulating frequency that's being sent down the gate as an AC voltage. So if this device is truly nonlinear, we should be seeing frequency mixing between these two tones, and that's exactly what we notice with our spectrum analyzer. So at the center, we have our carrier frequency, and we notice the appearance of sidebands at exactly the modulating frequency that we've set with our AWG. And we're attributing this nonlinear mixing to be coming from the quantum facelip capacitance of the nanowires. Now that we have a capacitive nonlinearity that we can work with, there are two directions that we can take with the same exact device. Again, the first one is to look at how the resonance frequency can be tuned, but then we're also going to see that providing a pump tone is leading to some parametric amplification of the same device as well. We'll start off with the first part, voltage tunable resonance frequency. So the experimental setup that we're using is a homodyne lock-in detection scheme shown over here. We're sending an RF tone to the device, and we're still supplying that AC frequency to the gate contact as well. Now, what the lock-in picks up is X and Y quadratures, or equivalently the magnitude and phase, and the resonance feature that we see in our lock-in amplification is shown to the right over there. So in the magnitude, we have two clear distinct peaks. The null point between that is the resonance frequency, and the phase response has a clear pi jump that we're also attributing to be from the resonance frequency as well. It's worth mentioning that all of this is taken at a static DC operating point, And the question that arises is what happens if we also start sweeping the DC voltage in addition to the AC that we're providing? Once we start doing that, we notice some modulation and periodicity appearing in our phase data. And it's more evident if we take a fixed frequency slice of this. And here we can notice a clear modulation of the phase response as a function of the gate voltage that we're setting, the DC gate voltage. The previous slide, I also showed you that we can track the resonance frequency. And if we use the same method at different DC operating points, we can extract the resonance frequency tunability of the same device shown to the far right. So we can see with this particular device, we get a tunability of around 1.2 megahertz as a function of gate voltage. So this was the first instance that showed us that we have a resonator that's tunable. And at that point, we can also move on to seeing whether this can be used for parametric amplification. So we revisit the same experimental setup. And in addition to what we had before, we're also providing it with a pump tone. This pump tone is actually going through the feed line as well. So what we're expecting to see is 4-wave mixing. And with this is sent at a particular pump frequency. And with the magnitude data that we've measured with the pump off to the left and pump on to the right, we'll notice some distinct regions that are appearing to be a little bit brighter, but it's a bit more evident if we look at the ratios of these magnitudes when the pump is on and the pump being off. And if we do that, we see a bit more modulation appearing over here. So there are some distinct points where the amplification that we're seeing is heightened and increased as a function of gate voltage. And then there are some other regions that we're noticing that the amplification is being suppressed at particular gate voltages as well. So to sum up what we've shown you today, we've presented you a device which is a quarter wavelength resonator with 2 quantum facelift nanowires embedded within it. We've shown that the resonance frequency is in fact tunable, and we've showed some initial results showing that the gain that we're seeing can also be tuned. In terms of the next steps that we're looking at, we've demonstrated 4-wave mixing, but we also want to be taking a look at 3-wave mixing, which we can do with the same device. So we want to be providing the pump tone directly to the gate contact that we've seen before. And we also want to be improving the fabrication parameters that we have, so optimizing the amount of resonance frequency tunability that we're seeing, but also the gain that we're seeing as well. Once we've done that, we're in a good position to be exploring some more sophisticated amplification or quantum amplifier setups like the one shown over here. We have a quantum facelift traveling wave parametric amplifier. It's also worth mentioning that other members of our group are looking at hybrid devices, which are not only incorporating these quantum facelift nanowires, but Josephson junctions as well. And this is effectively providing us a way to have access to both charge and phase degrees of freedom within the same device. That being said, that concludes my talk, and I'd like to thank all of our collaborators for making this possible, and thank you all for your attention.
Thanks so much. Questions? Yeah.
Is there any advantages or difference from compared to the conventional amplifiers using this duality?
Yeah, so we are hoping that with things being voltage tunable and electrostatic, you don't have to worry about flux lines or magnetic fields anymore. And that could be beneficial for a lot of communities that have, let's say, qubits that are sensitive to magnetic flux, for instance, the spin qubit community or some of the superconducting architectures that we've seen.
How uniform can you produce these nanowires, and how would it be visible in your data if they are not uniform, the 2 nanowires in the device?
Yeah, that's a good question. And you'll notice from the community that's explored this, yield is a key issue at the moment. So in fact, these nanowires, the faceslip energy and therefore the faceslip rate that you get from them exponentially depends on the dimensions of your nanowire. So the slightest bit of variation could lead to big differences in terms of what you'd be expecting versus what you experimentally measure. Now, in terms of the yield that we've had so far, it is fairly low, but there was a poster yesterday, and my colleague is here focusing on the fabrication side that can speak a lot more in depth into what we're trying to do for that.
Thank you.
All right, thank you. we have to move on, but thanks so much. So our next speaker is Yan, talking about data efficient inverse design of RF filters.
All right. So should we have the slides? Yeah, here. Yeah, here. Okay, good. So, good afternoon, everyone. My name is Ian. I'm a RF engineer from Scaling. So my topic is about the data efficient multi-fidelity inverse design of RF filters for quantum control systems. And in this work, we achieved to reduce the required EM simulations by up to 50-fold in the filter design tasks. So in superconducting quantum processes, the number of required low-pass filters grows with the number of qubits. Although we do not need one unique design per qubit, but the design goals depend largely on the system. For example, the qubit frequencies, the thermal budget, and packaging constraints. So to scale up the system, we'll meet the challenges in like limited space, which we prefer more and more compact designs. That's why we need a scalable and agile design pipeline. So let's compare different design methods. Traditionally, the hand tuning and the trial and error loop is time consuming, and the outcome might be far away from the global optima. Then with the help of inverse design and the surrogate acceleration, we could accelerate a bit the design workflow. So apart from that, the full pixelation allows us to play with non-intuitive near-arbitrary geometry, which might be the most promising way to achieve the best possible design. That's the reason why we stay with this QR code-like topology in our study. However, to training a surrogate model might be very data demanding. In our context, a surrogate model simply means a model which can predict the EM behavior of a certain type of EM structures. So as we can see here, even with very high performance computing hardware, like hundreds and thousands of CPU cores, generating data can be very time consuming, not to mention that with normal computing hardware, the time budget might become unacceptable. So this is where we ask ourselves, can we make neural network assisted inverse design more data efficient? So to answer this question, we took advantage of analytical EM simulator, which is designated for pixelated RF structure and with significant simulation speed up. Then we came up with the idea that we can use multi-fidelity approach inspired by transfer learning. Like we can use a large cheap data set to pre-train a model, then refine it with a small amount of expensive high fidelity data. So our plan is we first pre-train a neural network surrogate on large scale data set generated by analytical simulators. By doing so, we could obtain an EM-aware based model. Then we could fine-tune this model with small-scale, high-fidelity data set generated by full-wave simulations. Note that this whole workflow, we made it fully open source in the hope of ensuring the reproducibility and accessibility. So we first compared the results from analytical and full wave simulations. We chose a grade of 8 by 8 to make our life easier. And in the case of 254 micron thick substrate, we could see that the analytical simulator predicts quite well. However, in this case, the electrical length for a good design in the low-pass filter in the frequency band of our interest is not long enough. So we doubled thickness and redo the test. Then we found that the analytical simulator might not perform that well, but no worries. Later we will see that even with this large prediction error, the transfer learning still works. So once our simulators are ready, it's time to generate data. We fix our substrate thickness to 508 micron with 8 by 8 grid. We chose the QR code style random pattern, and 50,000 low fidelity samples were generated during 1.5 hours, while 22,000 full simulations took around 2 days, even with multi-process. And we extracted 4,000 high fidelity data out from this 22,000 to evaluate our surrogate model. Now now we will see step by step the benefits from transfer learning. So in this figure, the x-axis is the dataset size for the high fidelity data, and the y-axis is the root mean square error, which is defined like that. So the first thing to notice is the blue dashed curve here, which is our baseline trained with pure high fidelity data. Then let's take a look at the models before transfer learning. As we use more and more low fidelity data samples to train, the prediction accuracy becomes closer and closer to the performance limit of the analytical simulation. This is as we expected, and compare this performance to the baseline here, we could say that the analytical simulation actually provides good backbone for the transfer learning. And once we started the transfer learning or the fine-tuning the model, we could observe an immediate and remarkable root mean square error reduction with only 100 full simulation samples. And that means our transfer learning approach actually works. And in the end, we came to the conclusion that our multi-fidelity approach or models could achieve the same performance with much less full simulations. So in this work, we found that the model could achieve the same performance with only 200 high fidelity data samples compared to 10,000 in the normal training method, which is a 50-fold reduction. And this reduced the data generation time from to a ratio of over 1/16. And these benefits actually allows us to do the inverse design even with normal computing hardware. And we also did a simple demonstration for our inverse design workflow. The design goal is a 9 gigahertz low-pass filter. We chose genetic algorithm as our optimizer, and we tested 2 different grades, which were 8 by 8 and 16 by 32. And with only 300 iterations within around 10 minutes, we obtained these layouts. And these results show that our multi-fidelity approach or inverse design workflow actually can provide reasonable designs, and the prediction accuracy of our model is acceptable. So to sum up, in this work, we fully open source our low-pass filter inverse design pipeline was successfully built, and we have proved the potential of transfer learning enabled by the analytical simulator. And we did a simple validation with a demonstration, and we believe that this whole pipeline could be a useful tool in quantum RF filter design. Okay, these are the references, and I would like to thank Chairman for providing this excellent research environment and computational resources and academic support. Special thanks to Professor Yang Guang. And of course, thanks everyone here for your time and attention. Thank you.
Thank you. Questions? So maybe a novice question. So what's the use case for these quite wild-looking filters, like this QR code style? Is it like to make some really specific, complicated transmission spectrum? Or
okay, thanks for the question. It's like about towards more like scalable and agile design workflow, because nowadays the design might took a lot of like iterations and the time. Then if we could make this design more efficient, and then maybe for scaling up the quantum system, it might be useful. Yeah, that's the point.
All right, thanks. Any other questions? Oh, there's one.
What I understand is that the low pass filter has a different stage, or you can have different complexity on the low pass filter. So what's your kind of method can tackle the generally all the complexity, or is some specific stage? For each stage you need to simulate or run this method once?
Well, I'm not an expert in this cryogenic quantum computing system, but I would like to say that with this more efficient design workflow, we can separate these stages. We can make it like different models for different designs. That's a way to tackle this problem. Or maybe we can with more advanced mode like a neural network or efficient or accurate prediction, like with a more generalizability of this neural network, we might use only one model to achieve all these designs. Yeah.
All right, thank you. Yo. Oh, no, sorry, the other tab. Okay, yeah, just the keys here. Okay, last talk of the session, Arto Rantala, my former colleague, talking about experimental cryogenic RF switches for reconfigurable control of superconducting qubits.
Okay, so my name is Arto Rantala, and as Jonas mentioned, we are old colleagues from the VTT side. Now I'm on the company called Semicon. So, and in this my talk, I'm talking about the development of the Semicon company in the cryogenic switching, RF switching especially, and also what are under our development, and also our visions about the future. So the Semicon is located in the south part of the Finland, in Espoo. So there is a ecosystem around the university and VTT, having the largest clean room area in the whole research clean room in the whole Nordic countries. So we have a nice house supporting the wafer level processing of several different technologies, CMOS, MEMS, photonics, etc. So CMOS Semicon is really the hardware processing company. So we do have our own CMOS process line in the Micronova. In addition to that, we do have facilities to make the cryogenic measurements in the nearby on the Otaniemi and also the office spaces. So the Semicon is the startup from the VTT, 3 years old, increasing rapidly in the development and also the personnel. So even the figure here, it's outdated. Nowadays there are around 40 people in the company. So the company is really multi-talented. So we do have our own process capabilities, own designers, own measurement people. So for example, I'm IC designer, so we do have all the design capabilities in-house. So I would like to thank all the people shown here in this figure, because they have been part of the development we have done in some part. So about the Semicon's vision. So there are lots of challenges when scaling up the QPUs or putting things inside the cryostats. So as we can see in the booths, there are lots of people making lots of wiring and very complex things. So this is something usually you can see, and there are lots of problems or issues when you start to scale up things. There are lots of wires, thermal load to the cryostat, increasing the complexity, limits the scalability in some point, and also there is always latency between the room temperature and the cryostat. So Semicon's main idea is to integrate more inside the cryostat. So we have been starting in these current technologies, I/O, multiplexing, DC, RF, things that one can easily decrease the number of the wires. Later there is in this R&D part, we are putting more. So there are plans to put the digital microcontrollers, AWGs, and many other things. We are having our collaborators to integrate something together with our technologies, like a QPUs, and also the several different type of the sensors in the cryogenic applications. So about this I/O and the MOOCs and things. So here is one example of the Semicon's ideas and offerings. So having a platform that one can have connectors, PCB, silicon board, and system on chips package in one package. And here one can quite flexible manner mix with the different technologies. So all of those different technologies can be combined together with the one silicon board. So you do not need to integrate everything in one chip. So the very core of the Semicon is millikelvin operating in-house cryo-CMOS technology. So while in many cases people are using the standard CMOS and trying to utilize that somehow operating in the cryo, so in the Semicon we have developed dedicated cryo-CMOS technology. So really operating, fine-tuning the parameters in the process line to be able to operate in a millikelvin and have a very good performance. So when operating in the low temperature, we can we can push the supply voltage is extremely low level. We have demonstrated transistors down to 100 millivolts, and also the increasing the mobility 10 times comparing to the room temperature. And when having your own technology, it's also possible to add different layers, different things to the technology that are not allowed by the standard CMOS, like superconducting materials. So here is more detail about this 3D integration. So in this figure, there is one of our application having the silicon board and different type of the chiplets there. So this chiplet is very beneficial in a way that one do not need to process all the things in the same die. So one die can consist only the superconducting devices, while the other are CMOS. So one can really optimize those and connect those together in a means that provides a good thermalization and good contacts, for example, the RF and DC. So we do have a quite good variety of the different materials that can be processed in the technology, either superconducting or non-superconducting materials like a gold plating or indium for the bumps. So here is one example of the chips or chiplets we have processed. So there is a platform that having a multiplexer chip. So we integrated a multiplexer having 4,000 different pixels, and out from those one can multiplex in the 16 channels the analog signals out. So this is the platform that one can in a very efficient manner use the mass characterization of the devices. So this specific platform was designed in order to be able to, with a one cooling cycle, characterize lots of devices by multiplexing those out. While this platform can be modified in a way that to be able to multiplex several signals out of the box. So you using as a generic multiplexer of the inside the cryostat. And this can be either wire bonded or 3D integrated. So here in the bottom figure, there is another offering of the semicon. So there are quantum dots. So there was also example of the in this multiplexer having a quantum dot devices integrated inside the multiplexer. About the RF. So here is a demonstrator chip we made in the RF switching. So this specific device has been designed to provide a high current. So that can be used, for example, the flux bias. And in this case also one design parameters was high voltage. So this design can handle up to 40 volts in the RF line. And the measured results were showing that in the ultra low temperature, that was down to 430 millikelvins. The insertion loss was less than 0.6 dBs, up to 1 gigahertz, while having isolations over 60 dB until slightly over 1 gigahertz. And the DC resistance that was able to measure was something around 10 ohms, but it's still going down when decreasing the temperature. So in this specific device, the control is still in parallel way, but in future we are planning to have the digital control in a way that one could control several of those switches with a few lines only out from the cryostat. In addition to those RF and DC devices, there are development in semicon for the memory devices. So the memory is one component that one really needs when controlling larger systems. And the benefit of the cryogenic is that the leakages are extremely small, meaning that the DRAMs becomes extremely long retention, but this is just an add-on. So about the future. So future we are putting more effort to go in higher frequency, higher count of the signals in order to really be a solution for the RF switching. And here is our vision slide to in one day, not necessarily in the near future, but one day to have a fabric, cryogenic switch fabric between the controllers and qubit array. So there would be a dynamic allocation of the control and readout resources. Okay, so the conclusion is we have demonstrated RF switching at cryo quite a nice performance. We do have plans to go forward and really in one day to having a platform for the RF switching in a high number of the channels. Okay, thank you for attention.
All right, thank you, Arto. I think we have time for one quick question. So I saw in your RF switch, the performance seemed to start to deteriorate somewhere around 1 gigahertz. Like, why?
This is something that we will address, and most probably that will be solved by the better packaging.
Okay.
I also have a quick question. It was a bit hard to see, but can you say anything about the circuit topology of your RF switch?
It's a T-type switch. So having a series and shunt elements.
Okay, thanks.
All right, the talk was slightly too long, so I think we have to cut the questions here, but feel free to ask Arto later. Okay, and I think some organizer will tell us how to get to the dinner, so don't leave yet.
Hello? Yes, okay. All right, everyone, we are now at the final evening of the SQA conference. I hope you had a great day. Ahead of us now is the conference dinner. There will be many, many buses right outside the rotating doors to get you to the venue, where we'll have drinks, food, anything you need, comfortable seating. And there will also be some buses taking you back after that. The buses will leave in approximately 15 minutes, so please make sure you don't miss them. All right, see you there.